Yeah.
Okay, so with this, let's start. I'm the chair of this morning session. My name is Rafael Perkins, and our first speaker. Nice to meet you. So from for some reason we're buying champagne. So, but wait, Rafael, your time. So 30 minutes, and I will show you 5 minutes, and then 5 minutes for questions.
Thank you very much. Thanks so much for the organizers. And I'm not one of them, just so a few people were thanking me. I was just chairing the session. Thanks, Natasha, Andre. Thanks, Oscar and Hart for inviting me. It's really a great pleasure to be here. So I want to talk a little bit about nematicity, and I will promise to make connection with twisted stuff. But first, let me just acknowledge my collaborators. So I'm mostly going to talk about these works here, especially these first three. These first two were led by my postdoc, Joe Mies, and this one by my former student, Virginia Gali, that is now in Berlin, and Matthias Hecker, who is in Germany. And also going to mention briefly work that done with Anand Rastogi, who is my student here in Minnesota, and Daniel Echterberg in Milwaukee. All right, so I know that electronic nematicity has been discussed before. I just want to approach it from a more phenomenological and general point of view before I talk a little bit about what twist can do for you if you are interested in nematicity. And then I want to switch gears a little bit and talk about some fundamental aspects of nematicity that are related to the fact that it couples to strength. All right, so at this point, I think everybody here knows that nematicity is just a very broad word that means that electron degrees of freedom spontaneously break a rotational symmetry of the system. Okay, and it has been observed in many materials. I'm listing a few here. Iron-based superconductors is where I believe that you have the most many experiments where you can test a lot of these ideas, but it has been seen in as a vestigial phase of superconductivity in cobalt-doped bismuth selenide, twisted bilayer graphene. Jane yesterday talked about twisted trilayer graphene, so I'm going to update my slide later. But there are other materials that are nothing to do with superconductivity. Thulium vanadate is a very nice one. It's an insulator. And these van der Waals materials, they have this triselenide or trisulfide. Actually also show very beautiful paper here by several different groups showing that. So when I wanted to think of this problem more broadly, then instead of thinking of a simple material, because it appears in so many different contexts, I want to understand this from a broad perspective. And there is one issue that all of us have been dealing with since we started thinking of nematicity. It seems to be a contradiction. If you look at I'm going to use iron-based superconductors because this is where most of the detailed experiments have been done, but it's not particular to that. If you look at the transition, it looks very nice textbook mean field transition. By that, what I mean is that if you look at the susceptibility, which you can measure via elastic resistance, Raman, or shear modulus, it looks very much like a Curie-Weiss behavior. And I know that one exponent is not enough, so you can also look at the correlation length that you can measure using X-rays or neutron by looking at the sound velocity or corrections to the sound velocity. And there it also looks like very nice, proper behaved mean field transition. Okay? But at the same time, when you look down in the microscopic scale, and people can do that using, for example, local probes like NMR or STM, you start seeing what actually looks like the state of a random field Ising model. You see a lot of domain breakup. So it's kind of, it is very puzzling. How can a system at the same time display all the properties of a mean field transition, but then when you look down in the microscopic scale, you see behavior that is very much what you expect from having random field destroying everything. And it's not surprising that you have random field because random strain is present, right? So this is one of the mysteries that I'm going to try to convince you that I think we understand now. To do that, again, I'm going to approach the problem from a phenomenological perspective, from a field theory perspective, because I want to apply this to more than one material. So a very brief introduction. I know the experts here, they know all of these, but you can take a nap now while I explain that. What is the nematic? So as I said, you want to break the electronic nematic breaks translational symmetry, and this is done by electronic degrees of freedom. If you go back to classical nematics, which have been studied for before I was born, so to use a sentence that people have been using, they shouldn't in this conference. We understand that it comes, you define a director, which is a vector, if you wish, is an arrowless vector. And the key point is that nematic, it doesn't matter if it's up or down. There's no real arrow. So the only way you can construct an order parameter is by having a rank 2 tensor. And this is what is well studied. The D here, you can understand as a direction. Q is the order parameter. D is the dimensionality. This is just a rank 2 symmetric traceless tensor. In 98, Kivelson, Fradick, and Emery put out this idea that you could also have this in the electronic degrees of freedom. And we now understand that this can appear from a variety of different degrees of freedom. It can be charge, it can be spin, it can be superconducting. And again, all I'm going to say, it doesn't matter what's the mechanism, but I would just, for definiteness, consider the case where it's from the charge degrees of freedom. So you see, it's very similar to the definition that you had before, but now instead of the director, you have momentum, or derivative, if you wish, okay? And this paper here by Oganesson, Gibbons, and Fradick can set out the stage for that. But what does it mean in practice? Well, all of these expectation values are nothing but expectation values of charge quadrupoles, okay? And now, depending on the dimensionality, you can have different possibilities. So the problem that has been studied the most is when you have 2D or quasi 2D. In this case, you can write down the tensor, and there are two independent components, and we understand very well what they are. They are just charge quadrupolar expectation values of just which you can associate very clearly with a Pomerantchuk instability, where you get a circular Fermi surface can distort in ellipses. One mode is, you can think horizontal, the other is diagonal. So you combine them, you can rotate these ellipses in any direction you want, okay? So what we do usually is just express this in a basis, which is, in this case, Pauli matrices. And then we can think of this as a two-component vector, right? And that's my director in this electronic nematic space. You can follow everything we know from classical nematics, write down your action, and in 2D, something special happens that the cubic term vanishes, and then you have a second order transition, right? So the proposal back then, almost 30 years ago, was to get a nematic phase where in 2 dimensions, you can only have at 0 temperature because, again, you have this continuous symmetry. And then you're going to have a critical phase with quasi-long range order and separated by a BKT transition, okay? So far, so good. There are lots of interesting consequences. But in 3, and you can ask now, what happens in 3D? Well, in 3D, you can do the same thing. Just if you are, so as Andre likes I'm going to show some utensils of the theory kitchen for you, so you know we actually did something. But in 3D, you get 5 different components. And if you choose the symmetric gamma matrices, they're nothing but the 5 d orbitals, if you wish, okay? Just the form factors. Or if you want to be more formal, the L equals 2, we reduce presentations of the rotational group, okay? In this case, however, if you look at the free energy or the action, the cubic term doesn't vanish. You have a first order transition, and we're told since kindergarten that first order transitions are boring, so we don't worry about them. What I want to tell you today is that there's a fundamental difference, and we understand parts of it, and others we're still trying to understand. And it's because these electrons, they don't live in free space, but they live on a lattice, okay? And on the lattice, the key property here is the strain tensor. So again, strain tensor you define by studying uniform deformation, non-uniform deformations of your medium. You can define the deviation from the identity as a metric, and that's how you formally define the strain tensor. In linear elasticity, it gets this usual form here that we know, right? So it's just, again, derivatives of the lattice displacement. And what we know and you can just look, there are 6 components now. 5 of them are they have the same form as Nematic. It's a rank 2 symmetric traceless tensor. They correspond to volume preserving, but symmetry breaking deformations of the lattice. People call this in the elasticity community. I actually don't know if there is an elasticity community. To take these very old books, they call this deviatoric strain. And the one that is essentially the trace of this tensor is called dilatation. It's just a volume change that preserves symmetry. Okay, so here I'm showing the 3 modes that you get in 2 dimensions, an area change, or 2 area preserving distortions that break the symmetry. Okay? Now, what we understood from very early on is that because these 2 order parameters break the same symmetries, they have to couple linearly or bilinearly. And because of this bilinear coupling, so between the deviatoric part of the strain and the nematic, it means that whenever you have the Fermi surface distortion, your lattice is also going to distort. Okay, and this is for a while it's sometimes a source of confusion because you cannot have nematic without distorting your lattice. And then if you have an experiment, you have to ask yourself, how do I distinguish who is the chicken, who is the egg? I'll tell you who is the chicken, this guy here. But I don't know if that means that is the first. But what it means is that we know there is a very ingenious experiment techniques that were pioneered or proposed by Ian Fisher, where you can measure something called elastoresistivity, which can actually distinguish these 2 scenarios. And for all the materials I told you where this measurement was done, we know that this is driving and this is following. Okay, and I can tell you more later if you want. What I want to tell here is that, okay, we understand all of this, but strain is an interesting beast. It's interesting because strain is actually the theory of elasticity, the field theory is a tensor U1 gauge field theory, very much like electromagnetism, but for tensors. And people doing fractons will immediately recognize that this is identical, the field theory for the field theory of fractons. So there's some special properties, there's some constraints that it has to satisfy. And one thing that I'm going to tell you is that when these constraints of elasticity coming from the fact that these are deformations, that they have this gauge description to them, will be inherited by electronic nematics. And that's going to change a lot of the properties of nematicity. That's the goal that I'll tell you. Okay, so I want to tell you first about uniform strain fluctuations and how to twist, get it, the crystallographic restriction theorem. So what do I mean by that? I'm going to separate. So this is the general coupling between nematic and strain. I'm going to separate into uniform strain fluctuations. By that, I mean Q equals 0. They are essentially a whole lattice distortion versus the non-uniform one. They're fundamentally different. So I first will study these ones, and then I'll go back to the more interesting, or not more interesting, but the additional case where these are non-uniform. Okay, so you don't need to follow this. All I want to say is that the moment you have this coupling, your lattice has lattice constants and elastic constants, that tell you the symmetry of the lattice. All the symmetries of the lattice will be incorporated by the nematic. The first fact that you find is that you get an all-to-all interaction between nematics that invariably leads the transition to be mean field. Okay, so this was recognized early on, and this is a well-known fact that if you couple to a mode that is peaked that is uniform, you end up having mean field transition. And then the other price that you pay for doing that is that now this very nice picture that I showed you, where you have a director with continuous symmetry and a free energy that depends only on the magnitude, is gone. You get anisotropic terms, very much like if you do Heisenberg and then you include spin orbit, you're gonna get spin anisotropy terms. And you can do this systematically using group theory, and you find that for all in 2 dimensions, there are 10 different crystallographic point groups. If you analyze what can happen to nematicity, you find that there are only 2 options, okay? they're going to be an anisotropic term that has this form. This form here is nothing but a clock term, an n-state clock term. And n has to be 2 or 3. 2 means that I have an Ising transition. That's the case of tetragonal systems or systems that have tetragonal or lower symmetry. Essentially, I'm saying that you can only distort the square by having a rectangle in 2 different ways. Okay, so the director is locked to 2 different values. Or if you have hexagonal kind of symmetry, you're going to have n equals 3. That's a 3-state POTS or clock. POTS and clock are the same when n equals 3. And again, because if you look at the triangular lattice, there will be 3 different ways you can distort. Okay. And this, for example, we know this is the case in twisted graphene, the 2 materials that I told you before, cobalt doped or superconducting bismuth selenide, iron phosphorus trisulfide, where this is the standard, the superconductors, pnictides, cuprates, and heavy fermions. What it means is that that phase diagram with quasi-long range order and soft fluctuations is completely gone. We know that for the clock model, when n equals 2 or 3, it's completely dominated by amplitude fluctuations, not phase fluctuations. So you can only get, again, you can get what we call a nice nematic, a POTS nematic. You have a nice second order transition. The POTS one at 0 temperature has to be first order, but at final temperature can be second order. And that's what you're stuck with. All that physics coming from quasi-long range order, nematic phase fluctuations is not possible to be realized in the systems, okay? And ultimately, if you go back to this derivation I mentioned to you that we did, is because of crystallographic restriction theorem, which says that I cannot have any rotation that is not 2, 3, 4, or 6. So it seems that, okay, well, it was a nice idea. We're in bad luck because of crystals, and we have someone to defeat. 5 points for those that know the movie I'm referenced to, and 5 extra points for who this person is. Okay, this is the crystallographic restriction theorem. Natasha will give $20 for those that get the 2 correct. So how can we defeat the crystallographic restriction theorem? Well, throw away the crystallographic, right? Quasi-crystals. Quasi-crystals are probably, I mean, I find one of the most interesting things that in condensed matter or in, I don't know, crystallography. Crystallography is pretty interesting anyway, but these are systems that have long range orientational order, but no translational symmetry, okay? And the beauty of quasi-crystals is that they are not restricted by the crystallographic restriction theorem. Perhaps the most known case that you probably learned at some point or seen some point is the Penrose quasi-crystal. We know now there are naturally occurring quasi-crystals. Actually, there's one that is really interesting, but we know that there's some interesting phenomena such as quantum criticality, superconductivity, and other things in quasi-crystals, okay? And with the twist, actually, there's a very nice recipe to create a quasi-crystal in your lab without actually too much work. So this goes back actually from this paper by Stampley in 1986, but a lot of people recognize this recently. If you have 2 layers, they have DN symmetry, and D is just the hydro group, and then you do a pi over n twist, you get DND, okay? You can show this. There's some nice papers explaining this. This means the following. Take, for example, tetragonal lattice D4. Okay? Take 2 tetragonal lattices, rotate them by 45 degrees. You're going to get D4D, which is actually not a crystallographic group. It is the group, it is actually a non-crystallographic orthogonal group. There is an 8-fold rotational symmetry. It is an improper rotation, but it's still not allowed by crystallographic theorem. And you may have heard of this because people are doing that for cuprates. Right? They take Bisco, which is a van der Waals material, rotate by 45 degrees. And there the idea is, if you do that, you get D plus ID superconductivity. You can prove in one line after you realize this that it has to be D plus ID because the D wave superconductivity in this group belongs to a 2-dimensional reduced presentation. Okay? So you can actually learn a lot and manipulate things that we know in new states. Okay? What I'm interested here to show how I can realize this nematic phase with phase fluctuations is two hexagonal lattices rotated by pi over 6, okay, 30 degrees. You can see here a picture. Y is a quasi-crystal. If you make the origins equivalent, you're never going to get the 2 points being on top of each other again exactly. So you get this incommensurability, and there is a forbidden symmetry. Now, say, can people do that? Actually, people have done that, and they continue to do this. So graphene back in 2018, before Twisted, well, I think it was before the paper, the discovery, but you can just take two graphene layers, twist by 30 degrees, and you get this very nice pattern of a 12-fold symmetry, as you'd expect for this dodecagonal quasi-crystal symmetry. There are recent papers on, I invented a new element, should be tungsten. Tungsten is selenide. I know Eslam is in this paper. I don't know if, but anyway, he can tell more about it. And actually, there's a very interesting recent paper by Liang Fu showing that if you have a two-dimensional electron gas, you just solve the problem of interacting two-dimensional electron gas in a confined potential, in a quantum well, you get a bilayer ground state, and the two layers are hexagonal. You get two hexagonal, if you wish, Wigner crystals that are rotated by 30 degrees. So you get that as a ground state of interacting electrons as well. Okay. So there's several new symmetries when you do that. The most obvious one is a 12-fold symmetry that is improper, so S12. What it means is rotate. So I'm putting the top and bottom layers as purple and green. Rotate them for 30 degrees respect to each other, and flip the layers to get the same thing you started earlier. Okay, that's a 12-fold rotation followed by mirror. That's what's called an improper rotation. But there's another one, and I used all my I used all the skills I had to make this plot. If you rotate by 90 degrees, you see that now the rotation by 90 degrees essentially exchange the layers. So you have an actual, even though you only started with 6-fold symmetries, you have an improper 4-fold symmetry that is a rotation followed by mirror. Okay. And it turns out that if you go back, and I'm not going to show that to you, you can use group theory, you can do a microscopic calculation. You find out that the nematic is actually now odd under this new S4 operation, so it cannot appear in cubic orders. And then you find out that the new term, the first allowed anisotropic term is a 6-state clock. Okay? And you may say, okay, big deal. You went from 3-state clock to 6-state clock. Good luck. But it turns out that the 6-state clock is very special, and it's fundamentally different than the 3-state. And this is known since the 70s by studies of the clock model. So we know that, so there are two energy scales. If you think of the clock model, there's one energy scale related to the binding and unbinding of vortices. And there's another energy scale. My energy scale is really an RG scale, but I think you can see where I'm going for, where the anisotropy locks in. And it turns out that at z equals 4, they cross. So when you have a 6-state clock, you first go to a BKT transition. The anisotropy is irrelevant, and you get actually quasi-long range order. You stay in this phase of quasi-long range order until you have another BKT transition to finally long range order. Okay? So this is the way to realize quasi-long range nematic phase fluctuation dominated phenomena in a crystal. Okay? Several interesting things here. And again, we did all the calculations. I'm going to just tell you the results. Happy to discuss how we did that. But you can show here that this, okay, we didn't show that they both end in a single point, but I can tell you arguments for why this is expected. This actually belongs to the XY universality class. And because at p equals 0, essentially you have an extra dimensionality, the clock term is dangerously irrelevant, very much like the Brazilian soccer national team in the next World Cup. You guys cannot laugh. I can. Who is the only one that can laugh? But anyway, so you get this pseudo Goldstone modes, and you get a very interesting non-Fermi liquid to Fermi liquid crossover, because there's a special thing about nematic phase fluctuations that they couple, even though it's a Goldstone mode, they do not actually couple via gradient to the nematic. And that actually brings us something pretty new, which it doesn't happen, for example, if you do magnons, because magnons are Goldstone modes that couple via gradient. You can actually look at this regime. You get nematic fluctuations that are, for all practical purposes, long range. There's no, I mean, they're quasi-long range order. And they're characterized by an anomalous exponent that continuously change from 1/9 here, sorry, from 1/4 to 1/9 here. And you can ask what happens if to my electrons that are coupled to these low energy modes. And again, I can tell you more details about it. What we find is that you actually open something that we call pseudo gap like, because if you call pseudo gap, people don't like it, so you call pseudo gap like. But essentially, you see that you suppress the density of states at zero energy, and you open these two finite frequency peaks. You don't entirely kill, so it's still, for all practical purposes, a Fermi liquid, but with this weird form factor here, spectral function here, which resembles stuff that Andre, Jorg, Tremblay did on phase magnetic fluctuations precursor pseudo gap, although here this comes from a different mechanism.
So, Rafael, what sets the scale for delta there?
Yeah, so what sets the scale for delta is essentially, yeah, I think, yeah, so let's see. You know, it comes from, first of all, is a thermal effect. So if you go at t equals 0, this just collapses, okay? But of course, we can never get to t equals 0 because we go to the ordered state. And it's essentially the stiffness, because this time here has a stiffness. This kappa here has this stiffness, the proportionality on it, okay? So that's essentially that. We did add here a lifetime of the phonons to mimic thermal broadening, but that actually doesn't change too much this scale. It's really set by the stiffness, or which we know in the end is related to eta, right? Okay. All right. So, you know, again, if you got the joke, which I know you didn't because no one left, we partially defeated the crystallographic restriction theorem by doing this twisting and going to quasi-crystals, okay? All right. You can do this, yeah.
Monty Python?
Very good. You got $20 from Natasha. But they all know you need to know who the person is. So almost there. You can do the same for 3D. 3D nematics, actually, there's nothing that prevents it from existing. In fact, there are two candidate cubic materials. These are both superconductors. Topological. This is, I think, a topological semi-metal. This here, I don't know why people don't study more material that has uranium, thorium, and beryllium, right? It sounds something that everyone would like to put their hands on, but it's a very interesting cubic superconductor that seems to actually be nematic as well. You can do the same. I'm just going to give you the results that in this case, cubic groups, you get Potts model instead of clock. And in all the axial groups, you get a clock model, okay? How much time do I have? No, you said I started late. No. You said that 7. Okay, see? So I want to tell you now about the non-uniform fluctuations, right? So to look at this, and I'm going to look in 3 dimensions, I want to separate the effects of breaking the rotational symmetry from long-range elasticity, long-range interactions from elasticity. So I will adopt what is we call the isotropic lattice. It's not a real lattice, but it's just a theory of elasticity that respects rotational symmetry, okay? So in this case, there are only 2 elastic constants, the Lamé constant and the shear modulus, okay? And you're already going to see here what makes the non-uniform fluctuations, the ones that depend on position, special. We write down strain as derivatives of a vector. So the vector has 3 components, but this tensor here has 6. Clearly, I'm counting more than I need. And that's not surprising. It's because of these derivatives, right? So I'm taking full derivatives of a vector field. This means, this is exactly the idea that I have this. When you write down elasticity, this is a tensor gauge field theory. For being tensor, it has different constraints than electrostatics. So to make the analogy clear, in electrostatics, this constraint of having electric field being a full gradient, of course, we know means that the curve is zero. In elasticity, the equivalent of that is like taking two curls, one on the left, one on the right. But the way that this is explained is in terms of this operation here is called the incompatibility relationship. The tensor, I'm sorry. And the fact that strain has 6 components, but in reality, they only have 3 degrees of freedom, gives that get 3 equations that are nothing but incompatibility tensor being 0, so that you get then back your 3 equations that we started with, okay? This is known since the 1800s by Sun-Venant, they go by the name Sun-Venant compatibility relations. I'm really about the 1800s. That's true. You can find this there. So it's well understood, okay? Let me tell you what this means in practice. Let me take the 2D case just because it's easier to visualize. I take the element 3,3 of the incompatibility tensor. It spits out a second order partial differential equation. This equation is telling me that fluctuations of, again, you have derivatives, so you need to be non-uniform. Fluctuations of strain that are symmetry breaking but volume preserving will necessarily generate, or almost necessarily generate, volume changing fluctuations. Okay? You can see that by, let's set, for example, this guy to 0 and just look at the relationship between the volume change strain and the symmetry breaking strain for a space, you get a non-analytic relationship. This means that unless I'm in 2 special directions, so it's this plot here, right? Unless QX is 0, so I'm having my fluctuations being, my modulation being along the main axis, KX or KY, unless I'm in that situation, any fluctuations of shear strain will generate volume changing strain, okay? You can actually see that if you just try to start with a square lattice and put a modulation, a shear modulation along the y direction, it's very nice. You can actually, so the lattice sites are initially in the gray positions, the new ones are in the orange, and you can nicely connect them and you get volume preserving changes. But if you try to do that along the diagonal, you immediately conclude that you have to also change the volume, okay? Okay. This is actually the reason why when you measure sound velocities, they're not the same along different directions, okay? That's the reason why. But what does it mean for nematicity? Well, nematicity couples to this, right? So now it's going to mean that if, let's say that I have nematicity in the XY channel, it means that if I look at the fluctuations going along any direction that is not the main axis, I'm also going to generate volume changes. Volume changes are energetically very costly because they cost bulk modulus, which is the biggest, usually the biggest scale elastic constant in the problem. So they will actually be massive along that direction, okay? So this generates a phenomenon that, again, it's called, people call, including myself, direction selective criticality. But again, it's the same, it's just the elasticity, the fact that sound velocities are not the same in all directions, it's just coming from the same origin, okay? But see that it's all static. I'm just talking about non-uniform, okay? So if you plot the nematic susceptibility, it means that only along certain directions, it actually diverges. Along the other directions, it remains massive, okay? So this has very important consequences for quantum critical points and so on. But this problem has been seen in different contexts. I'm citing some papers by Schmalion, Indra Paul, Marcos Garz, myself, where we saw some of these features, but we really didn't know where it was coming from. So what we did, and to solve this problem, is the following. I need to, when I write the coupling like that, I want to actually find a basis where I can separate the incompatible volume costing changes of nematicity from the ones that are actually very nice, compatible, and don't feel that. So we have the action, and if I want to solve it, I would have to impose 3 second-order partial differential equations as constraints. It's an annoying problem. Instead, what we decide to do is let's think similarly to what we do Helmholtz decomposition in electrostatics. Okay, we can decompose any vector as curl and gradient. We can do the same for rank 2 tensors. We can separate them into a compatible and incompatible component. And that's what I want to do. And Joe actually figured out this, what we call helical basis, that does that for you for free. You pay a price, but it's not that heavy price. And I'll tell you what. Since I don't have much time, I'm just going to tell you the spirit. The spirit is that you do for a local basis that for each momentum, you decompose in longitudinal and transverse, but it's a non-local basis because you change momentum, okay? In this basis, you get only 3 strain components, and you can show that you automatically satisfy the compatibility relations. If you want, these are the way that you define the tensors in this new basis, and you can now express the nematic in this new basis. Bottom line is that you split, remember I had 5 nematic components, and I split them into 5 different components. They, I write them as this beautiful form, but they really have highly non-linear, highly non-local behavior. But in this basis, this is the full theory of nematoelasticity when you integrate out elastic fluctuations subjected to this gauge. I'll just take 1 more minute. You'll find out that 3 of the components actually become massive. So even though we start with 5 components, when you go to the transition, only 2 of them are massless, and the other ones actually are not critical, okay? And you can actually find the mass. So this is the one that costs volume, and these other 2 are the incompatible ones. And I'm just going to give you so these are the 2 that are compatible that we call phi 2 and phi 3. And the bottom line is that depending on which direction you're finding, you're going to see that is a different nematic in the orbital basis. So that actually is the change of basis. So I know in that new basis which direction is solved, but I know that as I go along that direction, it's going to be one of different, it can only be one of those different nematic components, okay? That's where direction selective criticality comes from. One of the very interesting consequences of that is that, remember I told you nematic has this cubic term? Well, because of this term now, you can actually show that this cubic term does not immediately induce a first order transition. You still get quantum, or you still get a second order phase transition, which is fundamentally different from nematicity. And the other thing to finish this is that you now see that so these are incompatible strain patterns, meaning that if you try to draw, you see that it's not single valued. They can only be generated by defects, topological defects, dislocations, disclinations, point defects, okay? So what we find then is that when you have all these defects in your crystal coming from, again, things that are inherent to crystal growth, those only couple to the 3 components that are not critical. So what it means, and I can tell you more about it, these are just distributions of this in this basis. What it means actually is that you get long-range correlated random field disorder along transverse and longitudinal directions. But the reason why you see these 2 behaviors is precisely this. The coupling to elasticity essentially creates 2 soft modes that are completely protected from all these random strain that comes from defects. That's what they give the rise to this mean field behavior. The incompatible modes that are not critical, they are the ones that are affected by the random field, or not random, but the conjugate fields from defects, and give rise to this pattern. Okay? So we call this nematoplasticity because plastic deformations are the ones where you start moving these defects around. I'll leave with my conclusions, and I'll be happy to answer your questions. Thank you.
And 1 question and 1 suggestion. Question about critical phase.
Yes.
Wonderful phase diagram obtained by symmetry analysis.
We also had,
That was the question.
Yeah.
Did you or someone else did numerics with microscopic model to see what the width of this critical phase is?
No, we didn't do that. So what we did have a microscopic model where we put nematicity by hand. and then we couple the layers, and then we solve the problem of self-consistently the Landau theory. We get the coefficients. In principle, with the coefficients that we got, then depend on the microscopic, we could actually get this, but we didn't do because, as you said, to get that, the best way would be numerics.
Yeah,
right.
The danger is that
it could be
there,
yes,
but it will
exactly.
tend to -3.
Yeah, it could be small, absolutely.
And very quickly, suggestion. At one point, you mentioned that you got a pseudo-gap phase.
Pseudo-gap like.
Pseudo-gap-like phase. Fine.
See?
Fine. This is doesn't matter. This is, I presume, one loop calculation.
Absolutely, it's one loop calculation.
And the danger here is this: if you do self-consistent one loop, you don't get it.
Yes.
So the question is whether subleading self-energy and vertex cancel each other or not.
Yeah. Now,
for some cases, we know that they must cancel.
Yeah.
Some we don't.
I agree.
Basically, the suggestion is just to calculate subleading terms and see whether they almost cancel.
I agree completely. We looked at the vertex correction, but we did more of a estimate. I mean, not like a full-blown, self-consistent calculation. It looks like vertex corrections because it's a little bit different here that you have this anomalous exponent and the coupling is different. It's not like this usual gradient coupling. It's more a Yukawa-like coupling. It doesn't look like that it's going to have this canceling effect. But I agree with you. What we would like to do is like something like icon approximation, something.
No, just to see something
to get this full. Yeah, absolutely.
Your argument to get classical phase transition relies on the form of your coupling, right? Does it change if
which coupling?
Epsilon dot phi?
Yes.
Does it matter if instead of epsilon you couple to derivatives of epsilon?
Yeah, it does. Actually, you can't couple to derivatives of epsilon because those they actually behave as an electric field because the gradient of a string you can always map on it's called a flexoelectric effect. So you can't couple to nematic. However, if you have a ferroelectric transition, you know that this electric field, that the polarization does couple to gradients of strain. And these analyses of what happens there in these cases have been actually done. There's some nice papers from a few years ago by Littlewood and I forget the name of the person in Los Alamos that was doing that. So this idea appears there, but yeah, it would be a different class of phase transitions that is not nematic.
That also includes time derivative, right?
So time derivative is a completely different beast because then you have to separate. Then you have Hall viscosity. You have to separate dissipative and non-dissipative term, and that actually appears a lot in ferromagnets or magnetic systems. When you apply a magnetic field here, actually, you do get a Hall viscosity term. This was shown very nicely in a model in the fraction of nematic quantum Hall effect by Eduardo Fradkin, that you do get couplings to not string derivatives, but time derivatives of the nematic gives rise to Hall viscosity terms. This is all in the electronic sector, but they will couple to the Hall viscosity in the phonons, and they will allow this. This problem has not been studied to the depth of the static case yet, but it's an interesting problem.
The reason why I ask is because there are cases when you actually cannot couple to strain at the lowest momentum because
right.
because the physics of it is much different. You usually couple to derivatives of moment. So you couple to derivatives of strain instead
of time.
Sometimes to time derivative of strain too, yeah. Like for example, if you would just assume some coupling like this and just go to lowest momentum, do the calculation with phonons for attenuation coefficients, you'll get the answer that is just wrong. Because that coupling is actually to derivatives of momentum, not to momentum.
Yeah, no, but here's a little different because the symmetry only allows, this is the lowest order coupling that you have, and it doesn't vanish when Q goes to 0. That's the key point. And we can talk more about it. It's because the quadrupolar charge does not commute with the overall momentum. So you actually don't get a coupling like gradient coupling that vanishes when the momentum goes to 0. You get actually a new Kawa kind of coupling between electrons and those. It's a nice paper by Ashwin, and we can talk more about it if you want.
Okay.
About this, can you go to this phase diagram with maybe here is
this one?
yeah.
Mm-hmm.
you know, I'm not, it's kind of a naive question, but so I'm familiar with this sort of
Yeah.
two BKT just in the classical flock model as function of temperature. But just to understand, so you're saying these two BKT lines made at a single point, is that even just in a quantum clock model without fermions, or is this something?
So this is so okay. There are a bunch of people that looked at this in different contexts. This, I would say, right now is the proposed phase diagram more than one that has consensus. People have tried to do numerics. The problem is it's hard to do, T=0 simulations of clock model. Sandvik tried to do this in a very nice way where he changes one dimension to time to look at that. I would say that I don't know if this is going to be a single point here or if they may merge in a first order transition or what can happen. I think here's a lot of questions here. If, again, the naive expectation from without electrons, of course, when you couple electrons, I don't know what's going to happen. Unless they're insulators, then I can rely on the same, and they are nematic insulators. But in that case, that's the general expectation. And if it happens, this point here actually has an XY universality. But it's but only because I think actually I have this plot that answers this question.
It's mostly, this part was mostly classical.
It's it's classical, exactly. But again, there were these papers by Sandvik where he tried to do that to the quantum case, right? By mapping classical and quantum, by just actually looking at 3D and 2D. But just to answer your question, right? So what happens is that it's a dangerously irrelevant variable. So there are actually two different exponents. And what you find is that at the transition, it's irrelevant and you get to an XY fixed point. But below the transition, you spend a lot of time close to the Nambu-Goldstone, but then you have to flow to here, to the discrete symmetry breaking transition. So the transition will be XY, but there's no Goldstone mode because of this dangerously irrelevant variable. But this is all classical. The best we can do is map the D to D+1 and try to understand what the quantum behavior would be.
But in principle, if you would map it to the quantum problem, is it also related to quantum geometry?
I don't know. Maybe. There is clearly, because it's a bilayer in my case, yes, you're going to get the quantum geometry. I never thought in this way, but I'm sure you can re-express that in a very clear way with the wave function of the two layers, how they form the new states. Yes.
Would be the
Yes, absolutely.
Who's the guy in Monty Python?
You have to find out. Yes.
Show it again.
last
Huh?
question.
Show it again.
It's Brave.
Brevet.
Yeah. Yes.
We never met.
I heard he retired before.
So exactly about this slide with this helical basis, when you said you get 2 or 3 massless.
Three massive and 2 massless.
So this, I can think about them as 2 acoustic modes?
No, it's more like you have 2 transverse and the other are longitudinal, because these are not phonons that don't have any dynamics. This is all static. It's just that this relationship comes from the compatibility relations. So there's no dynamics involved. You can think of these 3 of them as this is longitudinal and these 2 are transverse in these bases, but these bases rotate. So this usually transverse longitudinal needs to be along fixed direction. So it's a little tricky. I don't think you can associate like that. I think the best way is really compatible, meaning the incompatibility tensor is 0, and incompatible, which can only be generated by defects. I think that's the clearest physical distinction between them.
We need to go on, so let's
Thank you.
again. Our next speaker is Moiré from University of Utah.
If you go to I would expect that 3 of them will be.
Orbital magnetic responses in correlated multiband systems.
I mean, because you had yeah, that would. Then I would expect to, but there is one.
I will speed up with the microphone.
Hello, everyone. First, I want to thank the organizers for putting together.
Maybe even up.
Can you hear me? First, I want to thank the organizers for putting together this great workshop and for having me here. I want to use this opportunity to share with you some new ideas and approaches to understand, to compute magnetic responses.
Okay, can you check whether the microphone is on?
Yeah.
So,
Okay.
It's up and speak up.
Okay. I want to share with you some new ideas and approaches to compute orbital magnetic responses in interacting multiband systems. So we have, like Jiankang have given us a very nice review of why orbital magnetism is important and why they are challenging to compute. So I will try to be very brief here. So it becomes increasingly important to get a quantitative understanding of it, motivated by the experimental observations in Moiré materials. For example, there have been model calculations of twisted bilayer graphene showing that the spontaneous magnetization can be tens of orders of the ball magneton, and also the in terms of magnetic susceptibility, the orbital part is much greater than the spin contribution. And this motivates us to get a quantitative series for those magnetic response functions for interacting electrons in multiband systems. However, it's challenging to do that. And there have been like earlier works, and we have seen from the earlier talks that using these approaches is hard to generalize to interacting systems. Since last year, there have been like new proposals to generalize it to interacting multiband systems, and there have been several works that applies to Hartree-Fock or mean-field Hamiltonian, and we have heard one talk by Jiankang, done by like the three authors in the audience, Kang, Wang, and Vafek. And in this talk, I want to develop a theory for orbital magnetic responses for generic interaction effects beyond the mean-field Hamiltonian. And I want to, so there are two important points I want to emphasize. So the first is that we need to respect the gauge invariance, and we have seen from earlier talks that one can try to write down gauge invariant Green's function and try to compute the thermodynamic potential in terms of this gauge invariant Green's function. So this is also the approach I will take. And another subtle and important effect point I want to make is that actually magnetic field is a non-perturbative effect even for very small magnetic, even when field is small. So first, let's ask, so for these orbital magnetizations, we want to understand, can they come from classical effects? The answer is no. So while that can be like orbital motions from the classical physics, we know that the bulk and edge contributions cancel. So in the end, we will not get any magnetization from classical physics. And when we think about quantum mechanics, we know that even if we, even in the weak field regime where the magnetic length is much greater than the lattice constant, the magnetic field can generate Landau levels. And in lattice systems, it can generate Hofstadter bands. But the point is that if we have a metal, then we should see quantum oscillations. And so that means that when we want to understand the orbital magnetism, so there should be two distinct regimes. When temperature is low, much lower than the cyclotron energy, we will see the energy has oscillatory behavior, and that's the quantum oscillation part. And when temperature increases, so this oscillatory part is suppressed, and we will see this smooth behavior, and those are the perturbative orbital magnetic responses. And then the question I want to ask is, can we develop theories to study these orbital magnetic responses for interacting systems on the lattice in the weak field regime, so we do not have to project to the exact single particle eigenstate basis, namely the Landau level or Hofstadter basis. And another question is that, can we distinguish this oscillatory magnetization and the perturbative magnetization conceptually? So these are the two questions I want to discuss in this talk. So for the first part of the talk, I want to show you how we can compute these perturbative orbital magnetic responses. So I will introduce a scheme to expand this thermodynamic potential in powers of magnetic field over temperature. And that means that those quantum oscillations can be suppressed exponentially. And then I will apply it to spontaneous magnetization and discuss how we can generalize the notion of orbital magnetic moment and barrier curvature in the context of interacting systems. And in the second part of the talk, I may not have time to go into detail, but I will try to flash some idea how we can capture the quantum oscillations using a low energy effective field theory. And we will see that those features in the important in the oscillation, such as the period and the phase shift, encodes the kinematic properties of the Fermi surface. And this second part of this talk is done in collaboration with Yuxue Wang, who is a faculty at the University of Florida, and many of you know him very well. Okay. So let's first discuss the first part. So I want to have a theory as general as possible. So then we can try to write down this thermodynamic potential in terms of the Ladinger-Watt functionals, and which is written in terms of the Green's function and the self-energy. So for the students, let me give you a very quick review of what is Ladinger-Watt functionals. So basically, we can write down this thermodynamic potential into three parts, as shown here. And the first part, the trace log part, is present when there is no interactions. And for the second two terms, so they depend on the self-energy effects. And for example, for the last term, it basically tells us how we can how to determine the self-energy consistently. And this is formed by a set of diagrams which are called two particle irreducible skeleton diagrams. So these Green's functions and the self-energies can be obtained self-consistently from the Dyson's equation, and also these 2pi diagrams. And here we will consider magnetic field effect. And it's easy to understand that magnetic field, different from electric field, it doesn't generate any temporal dynamics. As a result, we don't have to worry about the time or temperature degrees of freedom, and we can easily work in the mass-Borel space. And I will just assume for the rest of the talk that we are in the mass-Borel space. And what is important is that, so those Green's functions and the self-energies are bilocal functions in real space. And for simplicity, I will just denote them with a subscript 1 and 2 denoting the position.
Question.
Yes.
So just to make sure I understand, so if like in your Lagrange word functional, if you only consider like two particle reducible diagrams, then your Green's functions are the full ones, right?
Sorry, okay.
I mean, if you only consider two particle reducible skeleton diagrams in your Lagrange word functionals, then your Green's functions are like the full one instead of the bare ones, right? Is that correct or?
This is everything should be the full Green's function, and the self energy could also be determined from the full Green's function. And then what we are going to do is we want to get the result that respect the electromagnetic gauge invariance. Then we want to express these Lagrange-Watt functionals in terms of electromagnetic gauge invariant Green's functions and self energies. I will just call it EM gauge invariant for the talk. And also, and to do that, let's first say how to obtain these EM gauge invariant Green's functions and self energies. So we have so this is this has been known for many years, as you can see from the papers here, and it's also like discussed very clearly in Jian's talk. So let me just like recap the idea here. So the problem here is that when we have in the non-interacting Hamiltonian, so we so when we do the pulse, let me consider the tight binding model, and then when we do the as the gauge magnetic field through the gauge field using the pole substitution, we find that first it will break the translational symmetry because of the gauge field. And secondly, because the gauge field enters, it breaks the EM gauge. This Hamiltonian is EM gauge dependent. As a result, when we solve the Green's function using this Dyson's equation, we know that it should also be EM gauge dependent. And the way to resolve this problem is to realize that for all the bilocal functions involved in this problem, such as Green's function, self energy, and the inverse of the bare Green's function, so they can be separated into two parts. The first part is a Wilson line part, and the second part can be shown to be gauge invariant. And to see that, you can plug in this this rewriting in terms of the Wilson line and this prime function, which I will which are the gauge invariant function into the Dyson's equation, and then you can move the Wilson line or to the left, and you will find that you will get a phase vector that's essentially the magnetic flux, and also this function does not depend on the gauge. And this allows us to do Fourier transformations, and if we write it into the Fourier space, we will get this Green's function. And here, so this is in this Dyson's equation, so we will say that the original product now becomes a Moiré product, where this theta AB is encode the commutator of the mechanical momentum. And so in this way, we can kind of intuitively understand the physics as that we write this Green's function in terms of mechanical momentum. And because of the non-commutativity of the mechanical momentum, so we have to write the Dyson's equation in terms of the Moiré algebra. So this is essentially the same as what is presented in the earlier works, but here we just want to highlight that this Dyson's equation can be solved to all orders in the magnetic field, so this Moiré algebra. Okay, and the next question is how to write down those the thermodynamic potential in terms of this gauge invariant Green's functions. So it seems to me that this is a very non-trivial problem, and it actually took me the longest time to figure this out. So the problem is present already for the non-interacting problems when we write down the thermodynamic potential in terms of this trace log of the inverse Green's function. So we will realize that this has contains both the Wilson line and the gauge invariant part, but because of the logarithm, we don't know how to deal with the Wilson line. And the resolution is that we can actually express it in terms of a fermion path integral and use some ideas in the non-commutative coordinate to resolve the issue. I will not discuss that, but let me just show the result. And if you are interested in the idea and how it was done, I'm happy to chat later. And so here is the result of this of the trace log part in the thermodynamic potential. So we can say that it can be written in terms of fermion path integral in the momentum space. So it's like just like what we had for without a magnetic field, except two things. The first thing is that so in this fermion action, so instead of a normal product, we have to use a Moiré product I introduced earlier. And that encodes the derivatives to the that is depends on the magnetic field and encodes the derivatives. And the second ingredient is that for this, so we found that this term depends on a renormalized Hamiltonian. And this renormalized Hamiltonian can be written as a non-interacting Hamiltonian, small h, and also the self-energy in the gauge invariant formulation. So that means that if we know how to solve the Dyson equation in the gauge invariant formulation, then we can use this solution and apply to this equation. And using this idea, we can then integrate out the fermions, and this is the first part of the thermodynamic potential we got. And this looks not intuitive, but let me just try to write down this magnetic field dependent part in terms of operators we are familiar with. So for example, for the first order term, it turns out it can be written as operators of velocity and position. And we can also do the similar thing for the higher order terms in the magnetic field. And so this is about the term that's inherit from the non-interacting Hamiltonian. And there is another term in the thermodynamic potential, another two terms in the thermodynamic potential that contains the self-energy explicitly. And we find that those contributions to the magnetic field effect to these contributions can also be written in terms of gauge invariant Green's functions and self-energies. And so these are this general formalism, and I can stop here if there is question and continue. Yeah.
Is it similar as doing Hamiltonian mechanics with a non-trivial symplectic form?
I think I haven't done that, but I think there are some similarities. But the one sample thing is that from here we don't really know how to write down the Hamiltonian in terms of symplectic coordinates. So we have to, in my opinion, we have to derive it here.
Let's talk, because that problem people addressed in precisely in this context, actually.
Oh, really? Yeah, let's discuss later. Okay, so now let me apply this to the spontaneous orbital magnetization, which is a linear term linear in V term in the thermodynamic potential. So this is the general result we got. So the key point is that, well, there are in the intermediate steps, there are linear in B correction to the self-energy, but it turns out that those corrections just cancels, and in the end, the spontaneous magnetization only depend on the Hamiltonian and the self-energy at zero magnetic field. So this is as expected because we are calculating spontaneous magnetization. It should be just a zero field phenomena, but it's like a confirmation. And now let me discuss like how to understand this. So I will consider a Hermitian Hamiltonian where this H, remember it depends on both non-interacting Hamiltonian and the self-energy. So let's say that it is still a Hermitian with self-energy, and as a result, we can write it in terms of those block wave functions and the real eigenenergies. And here, note that these block wave functions and eigenstate energies can be both frequency and momentum dependent. And then we identify two contributions, physically distinct contributions. Either both of them are invariant under this phase rotation to the block wave function, and people also call it a gauge invariance in terms of multiband systems. And these two contributions are exactly the orbital magnetic moment generalization of orbital magnetic moment and the barrier curvature. But here, so both of them can be frequency dependent. And then if we apply this to the frequency independent self-energy, we can recover the non-interacting formula in agreement with earlier Hartree-Fock results. So this is what I want to discuss about perturbative orbital magnetic responses. How many minutes left?
Almost.
Oh, okay. Next, let me try to let's go back to the questions we asked earlier.
8 minutes.
Actually, can I ask a quick question, Andrea, for just a few
Yeah.
seconds?
Yeah.
About the first part. You consider spontaneous orbital magnetization. Where in the equations are the conditions for spontaneous orbital magnetization?
Oh,
The
it's
fact that the interaction should be large enough to develop it.
oh no, it's it's like so it's not discussing like how to develop this spontaneous magnetization. It's asking if the system is breaks time reversal symmetry spontaneously, say when we know what its Hamiltonian looks like the Haldane model or some interaction model, and then how to compute it.
So you build it in the H naught.
Yeah, yes. So this zero field, the point is that this zero field Hamiltonian tells us everything about this response.
You distinguish between kinematic and canonical momentum, right?
Yes.
You want to have the gauge field in the Moiré, right?
Yeah, that because it turns out that this P is a mechanical momentum, so that's why we can do it in Moiré.
Just to make sure, like that expression works for any Latinger word function that you use, right? So
yeah,
Hartree-Fock truncate some order.
Yeah. It's like you use the Latinger word functional to determine what self energies you want to include, and then you just apply here. Okay, so going back to the questions I posed earlier, so here we want to ask further, how can we separate the oscillatory part of the magnetization with this perturbative part? So as I have shown here, so in this approach I introduced, so they actually explicitly introduce a perturbative series expansion in terms of magnetic field over temperature, and that is why we cannot really see the quantum oscillation. And it turns out indeed, we need some new ingredient to see the quantum oscillation effect. And this is what I did with Yu Xue on developing an effective low energy effective field theory to capture the quantum oscillation effect. So let me first explain. So why I think we think that it's important to it's important and relevant to have a low energy effective field theory. So we know that for this magnetization oscillation, so they are exponentially suppressed when temperature is very low, greater than the cyclotron energy. That's a low, very low temperature energy scale in the semi-classical regime. And that means that it should be determined by the low energy properties of the Fermi surface. And however, in the past, we don't really have a like good low energy theory for these quantum oscillations. And that's why we want to ask, can we develop this low energy effective field theory for it? And the way to do it is to apply this fossilized effective field theory developed by DDMS, where one of the authors, Mata, is in the audience. So we took their approach. What we did is we took their approach and generalized to the case when there is a magnetic field. So let me just sketch very quickly the idea of this fossilization theory. So the question one want to ask is that we know what is the equation of motion of the distribution function in the semi-classical regime. That's just a Boltzmann equation. And then one can, and from that, one can say that this distribution function in time is essentially the co-adjoint orbit of the equilibrium ground state distribution and the group of canonical transformations. And then one can ask, can we write down the effective theory for these canonical transformations and such that its equation of motion is the collisionless Boltzmann equation? And it turns out that one can do that, and that is shown in Ullmann's work. And furthermore, we show that actually we can generalize it also to multi-orbital systems. And this generalization is exact if we can replace the if all the product between the distribution function and all these like free space functions is in terms of Moiré algebra. And here, this effective action essentially tells that is a mapping from the free space coordinate to the target manifold of the co-adjoint orbits. And next, what we did is that we can consider what happens when there is a magnetic field. So we essentially couple this action with an external gauge field and ask how to solve this problem. So it's not a trivial problem to solve if we in the original free space coordinate x and p. So as we can imagine, they are not really a good coordinates as a starting point when there is a magnetic field. What we find is that actually we can replace this free space coordinate in terms of the mechanical momentum k and the guiding center coordinate r here. And with that, we found that it's much easier to deal with. And by integrating the guiding center coordinate, we find the Landau level degeneracies. And by dealing with the Moiré algebra of the mechanical momentum in the semi-classical regime, we can do perturbative expansions to this action and get interesting results. So now let me summarize what we have. So we found that this when there is a magnetic field, this fossilization theory can be written in terms of chiral bosons. So the semi-classical picture is just a cyclotron motion around the Fermi surface, and this is a quantum action whose energy level is integer times omega c. And in this quantum picture, it basically tells us this is the particle Hall excitations of the Landau levels. However, we know that in this problem we should see the Fermi surface area somewhere. And so what happens is that in addition to this chiral boson term, there is an additional winding term in the action, and this winding term encodes a Barry phase term, and it encodes the area of the Fermi surface. And then we can solve this problem and find that for the 2D electron gas, it can match exactly with the the Littrich-Kotovich formula for quantum oscillations. And also, it shows the topological origin of the quantum oscillation as a Barry-Fitts term in the effective action. And also, I want to emphasize that going back to the goal of this work, so we of the work, so we can construct this Gaussianized EFT without really solving the fermion problem at all. And we can also generalize it to the multiband systems, and we find that this Barry curvature effects also shows up in the action for the quantum oscillations, and to the first order in the magnetic field, it matches with the known semi-classical results. Okay, so let me summarize. So here I have told you like two stories of how we understand orbital magnetic responses, both perturbative and non-perturbative effects, using some like field theory ideas. And so for the first part, so we have found like how to deal with strongly correlated multiband systems. And currently we are working on understanding higher order magnetic response effects, and also considering interesting strongly correlated models to demonstrate this like what we found like formally. And for the quantum oscillation part, I have shown that we have formulated a low energy effective theory for these quantum oscillations. Well, what I told you about is focused on like non-interacting electron systems, but there have been one work by Yuxian showing that it can also be generalized to Fermi liquids. And currently we are also thinking about like interacting electron systems in a magnetic field, and also how to review other quantum geometrical properties beyond the semi-classical regime via higher order Inti effects. So with that, thank you for your attention.
Questions? Okay, so maybe.
On the second part, I understand that's mostly Yushan work, but you're heavily involved anyway. Can you regularly extend this approach to include interactions?
Regularly.
Aiding interactions in a perturbative way.
So it's only in Jen's work is only for the Fermi liquids, because we know how to write down this effective action for Fermi liquids.
Then you write down effective actions actually as non-interacting particles with a normalized coefficient. Can you go beyond the
like non-Fermi liquids?
No, not only non-Fermi liquid, but including all corrections that come not necessarily away from the Fermi surface, but away from it.
I'm not sure how far we can go like from an exact mapping as we did, but I think if you when we can adopt this effective field theory approach and write it in terms of effective field theory, we can probably make some progress.
And also very quickly, in the first part, you said that linear term in B cancels out. What about that if you do conventional case when orbital magnetization is proportional to the field? How you get it? It should be linear in B term.
Oh, you mean the susceptibility?
Well, or magnetization proportional to B.
So that one, I guess what I need to calculate higher order effects. I don't see apparent cancellation. I'm still doing that part.
Yeah, just regular non-interacting fermions, Van der levels that magnetization proportional to B.
Yeah, like that's a interesting question to apply this formalism to that, because so as we can see that we don't have to consider vertex correction and self-energy like separately. So this self-energy effect also encode any vertex correction respecting the gauge invariance. So I think that could be a good formalism to think about this.
Yes.
Could you go back to the formula for the orbital magnetization in the first part.
Yeah.
Yeah, I just wanted to understand the formula better. So H, so what exactly is H naught in P?
Yes.
That somehow includes the self energy, the full self energy.
Yeah. So this H no this H
Yes.
so the non-interaction and self energy, but the self energy depend on B.
Yeah, and you said that in the formula at the end, you can use the self energy at zero field. So this is just the regular momentum.
Yes, right.
Yes.
So this say linear in B terms in the end cancels. So for spontaneous magnetization.
Answer that question. So in your formulation, can we include disorder? So that it all goes through H0 again. So
I think if it's not a magnetic disorder, I'm pretty sure it can be included. But if there is a magnetic defect, I'm not exactly sure.
other questions? Okay, if not, let's thank.
Yeah, go on, turn off that. Sorry, go on. Turn off. Oh, yeah.
Yeah, except that I did.
Yeah.
It's very nice to see you.
Yeah.
Oh, yeah, yeah, I was trying to coordinate things.
Oh, we're going this.
You know, if you want to lose people on our side, people already get talks about it, I think it's been nice, yeah. And I will try to see if we can get you that.
I mean, probably in the summer, but I mean, I can.
Oh, yeah. That'd be amazing. Okay, well, then you coordinate so far. Well, it goes well. Yeah. And then you enjoy your new life there. They're lucky that they're lucky. Exactly. I'm sure lots of people interested to want to come back. They're lucky that they have you there.
But I'll go.
That'll be fun. That'll be fun. I'm glad you went to review this. Now, what happened?
Version in the model.
And then ask. Yeah, great. Yeah. So we know the just the built the ads. I think just
It's nice seeing you again.
Yes, the first is yours. The point that you were using, yeah, do you want to use it? So I can imagine you want to
Yeah, but I would also focus.
That's better. For me. Yeah. All right. All good.
Oh.
Between the
Okay, yeah.
But anyway, you should
So what
and my experience first 2 months winning you fight. Let me talk with you. Be patient.
I can already kind of sense that. Yeah, patient in terms of, I guess.
Because we just gotta give you a little bit more.
If the value of the kind of chronic
Yeah, that's what
Yeah.
Let's just go for that.
Yeah. Okay, that's a great advice. Yeah. Okay. That's very important. Yeah. I was originally patients like them. Yeah. Seems to be a lot of bureaucracy that's like whatever. Reading virtue. Okay. Yeah. Y'all. You.
And you know, if you'd like, if you want to do that, any of them.
Oh yeah. Yeah. Oh, I.
Все
Yeah.
это делал
Yeah.
ровно неделю назад.
Я понимаю. Ну, это уже что? А?
Yeah, not even like specifically.
Здесь-то я что, я расслабляюсь, мне ничего делать не надо.
Yeah, so yeah. Yeah. Okay. Yeah, thank you. Yeah. Thank you. Yeah, sure. Thank you.
Yeah, well, I mean, isn't like, this, right? It says no problem.
Yeah. For how long you're staying here?
A while. Yeah, I mean, you play, see. Not just several people. So, I wanted to know if you have
We should take the most generic version of play. And work with.
Yeah, my black.
So. I realize we're not okay. Then, how does this way? You know where bait is?
Which was that?
Bait is building. Okay. The tooth is one next to this one. That's called PAM.
If you just
That's
want
not physics and non-physics.
the Z3 cross Z3.
If you want, I can meet you here at the end of the class. I'm bringing you the physics actually for these. So at 4, I will be at, there are 2 entrances, the ones that are closest to radio, the ones that you normally use.
Yeah. Somewhere that. Maybe you can also say. Maybe I'm not oriented.
Okay. The ones that we started gradient on one side and what I call PAM, physics and non-physics.
Should also make sure that that's on display.
You can still have delta alpha I, except now this may not be proportional to an identity matrix, so you may have to make it. Yeah. Just put it the level right. But I think the urgent thing right now is figuring out this positive versus negative L business. Yes, we should do the calculation. Oh yeah. So for just to bring it up, we were thinking because the microscopic lattice symmetry is only Z3 cross Z, which embeds Z3 cross Z3 into U3 flavor. There's no reason to have a full SU3 flavor symmetry. General situation. So the 3 flavors of quarks can have different like dispersions.
Right.
It doesn't necessarily.
SU3 flavor, you have, but instead of U3 flavor, you have U1 cross U1 cross U1 for each pocket. So U1 for each pocket, so U1 cross U1 cross U1. And then times SU3 gauge. What does this mean for the order parameter? Color flavor locking, and I suspect it means that alpha I can basically have 3 different diagonal components. Instead of having.
It's really okay.
I didn't write it down in my paper. I mean, it's this the whole stack. This is key.
Yeah.
But this is what I have in my note. Okay, so the key question you get something like that, and then because this is trace law matrix, so you can always be written like
Helps us from.
the inverted matrix. Then you will see this matrix, right? So now this you write this as AUR part.
Moment Wagner probably
Phase vector. Because you can understand this is trade basically the x y and x. This one is x y, right? So this give you a base. This give you a base. But this base like I think C. They can cancel with this one.
Yeah, that's not.
That
It's
everything.
not a paper of fine temperature.
Yeah. Yeah.
Which I think is much similar than what you have. They will
Probably.
Oh, I see. Yeah.
Well,
It is
but I
the
mean,
main
you didn't have this law in the graph. But other than that, this automatically becomes now you might
I finished the calculation last night for
because I know
the
this
sign,
this
but
one
I
is
was
just,
making sign errors, so I think it
well,
went to
Yeah, so I think, given that it's a sign.
Exactly.
That's like the most important.
But in your case, of course, you need to do it.
Yeah.
Because
Like for both of you.
Yeah.
But the skill.
Yeah.
The
And this is very
Yeah.
because there's a difference in terms of
And
how
you do
we,
this.
so we need people saying
Yeah.
P minus IP.
Then we use this story. So hopefully we anyway. 我自己我可以把知道还是否对。没有任何。
I always confuse which one is plus half and which one is minus half.
我给你提问了，我记
It's
得
the。same as.
我都删了，我微信全删了。Try to calculate it. 我反正不了，我现在我也不知道。
See how the contraction.
什么？这一门就是你们没学
sign would be.
我怎么知道你都
Basically, so the calculation that you did, you were looking at the sign of the tensor. Right. The part that depends on the current will also have a sign depending on what the value of the angle is. And this you don't have to do for all phases, just let's say for the color flavor locked phase specifically. So like what is the sign? I think it's going to be the current. What is the sign of the current depth for an angular momentum L?
Okay. I wanted how the reaction about it.
So it doesn't come in the Feynman diagram, but the if you look at the Ashwin paper, they talk about how to do that calculation. So you're assuming that you have a Cooper pair state. And you basically take the expectation value of that part of the Hamiltonian in the Cooper pair. So this is the Hamiltonian they're looking at, J times the interaction, and we will have a similar form, except instead of phi ij, we'll have some like color labor indices and everything. But this is their state. So it's a Cooper-Pevin state. So it's up in and then you take the expectation value of this Hamiltonian in this state. They find that it's proportionally signed. Oh, I see.
Okay, so try to see if this is true.
Yeah, I mean, you kind of compare what directed what they're doing. They're not trying to say words.
Yeah.
I mean, we already, so like infra pocket interactions for us already.
Yeah.
Okay.
Okay.
You know, not everything is identical, but theory is not identical.
That's it.
That's it. Okay. 我说的是你用那个分秒长一个的地方，应该中间不是它
Some level the like basic physics they're trying to describe in this very natural. Yeah. A lot of
we think we're looking at cases.
I mean, so we know that
然后前面要当然有
generally the ground states are these. So we have
这个一般都
so we have P plus IP for about that will be the same sort of thing. So it has to be the same, UV properties.
Yeah.
Sort of inward.
Important to me. Sure.
So that's our last session for today and for the conference. So the first speaker is Inti Sodemann, and he will speak of new gifts from cool gases to Laufman, BCS, Moiré states, and geothermal. So I will show you 5 minutes before discussion.
Yeah, thank you very much to the organizers for this opportunity. It's really fantastic to be here with this amazing group of people. Can you guys hear me?
Yes.
Yes, we can.
I'm kind of sad to hear that the funding is running out, but I hope you guys find some way to, keep this fantastic conference happening over the years. Yeah, so I'll tell you some story about, understanding of correlated many-body states by using some kind of new twists and new ideas of from Coulomb gases, okay? And this work, the part that is related to Laughlin states, has been driven primarily by Zaranjo, who's my postdoc in Leipzig, but also now we're doing some collaborations with my collaborator Tran in Lanzhou in China. And the part that has to do with Moiré states has been done with Zaranjo, but also in collaboration with these guys here. The part about Moiré is not published. The part of Laughlin is in this paper. Yeah, I'm in Leipzig. It's a place with very rich history, just about an hour by train from Berlin and Dresden. If you're around, let me know. It would be great to have you. And before I go into the main topic of these Laughlin states, I want to highlight some other work that is taking a lot of my brain power these days, especially because I'm here in Minnesota, which is, one of the powerhouses of experiments in this phenomenon called microwave-induced resistance oscillations in gallium arsenide. So I just want to flash this very briefly, okay? This is not the main part of the talk. It's just sort of advertising of another work. So this plot here is the resistance of the good old-fashioned gallium arsenide two-dimensional electron gas as a function of magnetic field. The red line is just the usual Shubnikov-de-Haas effect, okay? It's the resistivity in equilibrium as a function of magnetic field. This blue line, this true experimental data, is the resistivity of the two-dimensional electron gas when you're shining microwaves. It's amazing. Look at the huge differences just by shining microwaves. You start seeing oscillations way before the Shubnikov-de-Haas effect. Much bigger than Shubnikov-de-Haas. These are the so-called microwave-induced resistance oscillations. Since the discovery of this effect by, Michael Sudoff and other people, a few theories, several theories, I should say, came out. But I am on a quest to show that these people have been asking the wrong questions. And this phenomenon is actually much more interesting than what most people have so far realized, okay? So I call this very briefly the blind spots of Miró theories. Okay, there's nothing particularly wrong about them, but they just have been thinking about it, in a too narrow fashion, I would say. First of all,
even the name, just MIRO, microwave-induced resistance oscillations. Nobody seems to have asked the question, experimentalists and theorists, if there are oscillations of other observables. You know, in equilibrium, you see Shubnikov has, but that's just one oscillation, right? It's just the one that is easiest to measure. But, you know, we know there is oscillations of magnetization, the Husband Alphen, et cetera, et cetera. Any observable will oscillate, you know, as long as the lambda levels are crossing the chemical potential. Nobody has asked the question, are there oscillations of, say, the magnetization when you shine microwaves in gallium arsenide? What is the steady state at zero field? Is this a property? Does this oscillation have something to do with the steady state at zero field? Just like, you know, quantum oscillations reveal the presence of a Fermi surface. What is going on at zero field when you're just shining the microwaves on the electron? Which states are contributing? Is it states near the Fermi surface, deep states? Where is the bath? This is non-equilibrium physics. Doing non-equilibrium physics without baths is kind of nonsense. And most of these theories have ignored largely the issue of what is the bath to which electrons are coupled. Anyway, these are the blind spots of these theories. And I'm preparing a theory that's going to come up and it's going to revolutionize this, okay? So together with these guys, we have been playing with toy models for a few years. But now we're ready to go to the real gallium arsenide, put the bath on gallium arsenide. But what we have found is the following. Okay, so if you just compute very carefully the steady state of electrons, when you shine microwaves, they don't occupy states according to Fermi-Dirac. You solve the kinetic equation, and the steady state actually has a kink, a kind of emergent Fermi surface, a light-induced Fermi surface that appears when you cut the dispersion by the driving frequency. So MIRO is a kind of non-equilibrium Shubnikov Haas of this light-induced Fermi surface. Okay, coming up. It's still under preparation. This is too very. No, just kidding. Go ahead. Go ahead. Please.
We can.
This is a very long discussion, and I saw things, but please just go ahead.
Just saying, one is Shubnikov does is quantum. MIRO is classical.
It's quantum. It's quantum. Let me tell you. We can discuss. We can discuss. It's quantum. That's why it should be MICO. Microwave-induced quantum oscillations. Okay.
Just about what you're showing. So there's n of k, and then you're saying that there is a kink. What is a kink?
Occupation of states. How many electrons have how much in a given moment?
K by itself is regular.
In equilibrium, this would be the Fermi-Dirac function with just one jump at the chemical potential.
Mm-hmm.
And I'm saying when you solve the steady state occupation, it's a non-equilibrium Boltzmann equation.
Yes.
We do this numerically, you know, no cheating.
Mm-hmm.
You find a kink at a different momentum, different than the Fermi momentum that is controlled by where does the photon frequency cut the dispersion measured from the bottom of the band.
Mm-hmm.
Okay? And that's the light-induced Fermi surface-like kink that is behind MIRO. Okay, but now the actual talk, okay? Yeah, so the actual talk has two parts. This is a story that is inspired by all this beautiful recent work on ideal Chern bands that are relevant for, you know, Moiré materials that have displaced quantum Hall effect at zero magnetic field. And basically what I want to show you in the first part is that if you just write down the Laughlin wave function in an ideal Chern band, an ideal Chern band you can think of as a deformation of the usual lambda level. Even the ideal Laughlin wave function will have a phase transition. So the same wave function can describe different phases of matter. In the usual lambda levels is typically, I'm going to understand this by using a mapping to a Coulomb gas. And so in that Coulomb gas language, the usual Laughlin state is in a plasma, a kind of classical metal. And what I will show you is that by deforming the Landau level, I'll explain in a toy model basically what these axes are later in the talk, just to give you the punchline here. By deforming the Landau level into this Chern band, eventually the Laughlin state, even let's say at filling 1/3, will go through a BKT transition into a very strange state, okay? It's some state that has power law correlations, so it's gapless, but it doesn't break any symmetry. So it's some kind of gaplessness that cannot be understood with usual Goldstone mode point of view. So it's some strange power law correlated phase of the Laughlin wave function, the same nice Laughlin wave function, but now written in this deformed Landau level. And the second part of the talk is about P plus IP Pfaffian wave functions of BCS kind and the related Moore-Reed states in Landau levels. This part is actually just Landau levels, not even ideal term bands. The same, good old-fashioned Landau levels. So when we did this, we started thinking, okay, what else can we do? Let's try to think of a different state. Let's try to think about Moore-Reed, for which there is a plasma mapping that was proposed by Bonderson, Gurari, and Nayak. Wow, this is wrong. Sorry, I copied this. Sorry, there's a typo here. This is not the right year. Several years ago. The main message is actually that this plasma mapping that they proposed there is not completely correct. Okay, it does not allow you to compute the correlation functions of the Moore-Reed state in detail. Okay, it captures certain universal properties like perfect screening, which are necessary for what they needed to use that plasma mapping for. They were using it just to compute the statistics of the quasi-particles in the Moore-Reed state. So all of those conclusions are correct because the universal properties of perfect screening are still there, but the detailed plasma mapping that they propose is not correct. It needs to be corrected. Okay, and we have found a correction to that plasma mapping. And I should say the person who really, came up with the key formula to correct this, just to give credit, here very clearly, was actually Victor, okay? So my main job was to harass Victor for a while to convince him that there were problems with his old plasma mapping, and he eventually came up with a very clever way to correct it. So now we have, this is still unpublished, now we have a way to correct this plasma mapping. I should say that then the corrected plasma mapping does not allow to compute the correlation functions of a Moore-Reed state in detail. But when it's corrected, it maps to a more complicated wave function, a kind of mixture of bosons and fermions that I'll try to explain. Okay. Okay, so very briefly, the first part, let's just remember a few basics of Landau levels. So when you have electrons that are in the lowest Landau level, the single particle wave functions are essentially holomorphic. So you have, a holomorphic part, and all the non-holomorphic part is encoded in this exponential. And so the many body wave functions you can view essentially as a kind of holomorphic polynomial of n coordinates times this product of exponential for all the electrons. The Laughlin state is a very special kind of state. It's a state that is associated with a very special polynomial. So you can show that the number of zeros that this polynomial has equals the number of flux quanta. So this polynomial has to have a number of zeros in the plane, and the number has to be equal to the number of flux quanta. So when you're a filling factor 1/3, that means there has to be 3 zeros for every electron. The Laughlin state is the state that binds the zeros as best as possible to the particles. So it puts all the zeros on top of the particles. That means you have this kind of polynomial that's very good for keeping electrons away from each other. They have very good repulsive correlations as a result, and that's why it's a very good state energetically. And you can think of this sort of bound state of the electron to the zeros as the composite boson. And so from the very beginning in the paper by Laughlin himself, he pointed out something very nice, very useful, which is if you take the wave function and you just square it, you compute the probability density. This probability density is identical to the probability density of a classical StatMech problem, the one component Coulomb gas. Okay, so you can write it as the exponential of some classical energy at some temperature which is fixed by the filling. So this is a fictitious temperature. It's not real temperature. It's a temperature that is related to the exponent in the Laughlin state. The larger the exponent, the colder it is. And the potential is the potential of just point particles repelling with two-dimensional Coulomb forces, but in a neutralizing background that is uniform. It's a kind of two-dimensional Gillium model of the Coulomb gas, okay? And that was very useful for Laughlin to make several arguments. Yeah, so one important, let's revisit briefly the phase diagram of this classical StatMech problem, okay? So just one parameter, again, the temperature, which is essentially the filling. When the filling is high, you're in the plasma. That's the usual Laughlin state that we all know and love. At some very large value of this exponent m, when m is equal to the order of 70, actually that wave function has a phase transition. The wave function itself has a phase transition into what people believe it's a crystal, a triangular lattice crystal. This is known from, like, you know, classical Monte Carlo simulations of the Coulomb gas. But, you know, in order to have a topologically ordered state that is fully gapped, short range correlated, you really need to be in the plasma. The plasma and the perfect screening of the plasma is what guarantees that the state has short distance correlations, okay? For example, you know, if you just want to consider a quasi-particle, what you would do is you multiply the Laughlin wave function at quasi-hole by this extra zero, and then you can do the argument that that quasi-particle looks like a test charge that has a kind of mathematical formal charge, bare charge, so to say, of -1/m. So the reason, the physical charge of a quasi-hole is not this formal charge. This is just like mathematical trick. Okay, the physical charge of the hole is how much electrons come from the surrounding fluid of the plasma and screen it, right? Because there is perfect screening, the amount of electrons that have to come has to compensate this because it's a plasma, right? And that's why the physical charge of the Laughlin quasi-particle is fractional. The physical charge is just the screening cloud, not the bare charge. Okay, the bare charge is some mathematical kind of trick. Okay, and it's only quantized and only this, you know, nice fraction because of perfect screening. You know, what would happen here is not clear because that's not a plasma. Okay.
Question.
Yeah.
Can it be there another intermediate phase like a?
It is very complicated, and there's still some debate here of how this melts and so on. It's a low temperature.
Okay.
It's a bit complicated there, but it's known that there is some transition at very low temperature, and what it is continuous, first order, is still kind of very a bit tricky.
Whether it's relevant to the quantum Hall question, right?
Say that again?
Whether it's relevant to the quantum Hall.
Yeah.
The quantum Hall will go through transition to a big net.
Sure. A different question is, you know, a true ground state of Coulomb Hamiltonian, when does it crystallize?
Yeah.
This is when the Laughlin wave function crystallizes. That the true ground state of Coulomb crystallizes like at 1.7 or something. So for a long time,
state of electrons in a magnetic field.
Yeah.
This may depend.
But you know, so for a long time,
Yeah.
it depends on details. I'm just mentioning the one of Coulomb. You know, so for a long time, this was viewed as a kind of academic thing because, you know, like the real Coulomb, the electrons are crystallizing before. The Laughlin wave function is not a good approximation at such a low fillings. So kind of interesting but academic point. So anyway, I'm wasting too much time already. So fast forward to today, we live in the era of where our dreams of fractional quantum Hall without field came true, and, you know, thanks to the work of excellent work of many smart people, some of them here in the audience, we have now a kind of generalized notion of a Landau level that is believed to be relevant in these Moiré materials. That is what I call here, or what is called an ideal Chern band. Okay, so I want to kind of just here review very briefly the real space point of view of this ideal Chern band, which is most useful for the kind of things I'm saying. Okay. These ideal Chern bands are essentially generalizations of Landau levels in which the single particle wave functions are still holomorphic functions. Okay, all the single particle wave functions can still be written as some holomorphic polynomial times some kind of fixed rigid function, okay, that I'm calling here G, that is replacing this exponential, and that you have to figure out from, you know, problem to problem. It's something that is changing, you know, as a function of the twist angle, details, etc., different in one model or the other. But it's, you know, once you have a given model, it's a fixed thing, and it replaces this exponential. And the rest of the single particle wave function is this holomorphic part. a very simple kind of toy model of this is if you just take a Dirac fermion in 2 dimensions and you apply a magnetic field that depends on space, non-uniform, you can still get a perfectly flat 0 Landau level, but the wave functions are now this holomorphic part times the exponential of some scalar function that you need to solve by solving this Laplace equation with the magnetic field, okay? So for concreteness, we're going to kind of imagine this setting, okay, that we have a non-uniform magnetic field acting on some Dirac electrons, but you can also apply that to kind of figure out what that magnetic field is for your given microscopic Moiré model if you want to. Oops. And so the idea then is we can still write the Laughlin wave function, same principle as before, bind the zeros to each other. The only thing that changes is this exponential, and then we can still do Coulomb gas mapping. It's very easy. The square of the wave function is still a classical, StatMech weight. The difference with the previous one is that now this exponential turns into a non-uniform, a potential arising from a non-uniform background, okay? So it's as if you had the plasma, but now the background is not Gillium, it's some kind of potential that is changing in space and that, will depend on the details of your Moiré band, etc. Yeah, so here is an example of, some calculation of a paper where it shows this real space magnetic field. You can see it's very highly localized. This is for molybdenum ditelluride, so it's like some very tiny solenoids. It's really highly localized in space, okay? It can be, okay, in some settings. The Moiré unit cell carries flux one flux quantum, one effective flux quantum. And when you do the Coulomb gas mapping, the background, has a uniform charge that is tied to the number of flux quanta. So every flux quantum for the Laughlin state M carries charge plus 1/m. So it looks like an ionic crystal, but with a fractional charge per unit cell. That's how it looks in the Moiré case. So I'm going to do something simpler. This is a huge simplification. It might not be relevant to Moiré. This is something I'm still fully trying to understand. I suspect and I have speculations, but it's a toy model, okay? It's a huge simplification. I'm going to deviate from the Moiré setting. I'm going to be a little bit closer to what we had in the Landau levels at very large M. So the electrons are trying to form this kind of Wigner crystal, but the neutralizing background is just uniformly spread. So all I'm going to do, when you count the number of fluxes per unit cell of the Wigner crystal, because there is one electron, then there will be M fluxes per unit cell. Each flux has charge 1/m, so that means the unit cell, the background charge of the unit cell in the Wigner crystal is 1, okay? So let me just kind of compress that background charge into a disk. That means I'm just making the magnetic field come in like solenoids, okay? And I'm going to consider this problem. What happens to the Coulomb gas when now the neutralizing background is not uniform, but this kind of collection of solenoids? This problem was studied by, StatMech people a while ago, and they found this phase diagram. So the y-axis, so we have a triangular lattice of solenoids with radius sigma. The y-axis is the radius of the solenoid. The x-axis is the temperature of the Coulomb gas, which again is the filling of the Laughlin state. So when the radius is comparable to the distance between solenoids, we're kind of in the spreaded flux limit. So we're kind of back to the usual Landau level. And as we concentrate more and more the flux, we go farther and farther away from this usual Landau level into more these situations of very concentrated fluxes, okay? And what they found is that there is a Kosterlitz-Taules phase transition. So at high temperatures or, very spread flux, the electrons are ionized from these solenoids, from these ions. They are floating around forming a classical metal. They eventually cool into an insulator. So it's a classical metal insulator transition. The electrons bind to these protons, right? This is like classical hydrogen, and they form neutral hydrogen. And there is a sharp Kosterlitz-Taules phase transition between these two states. So it's a state that forms a dielectric now. It's an insulator, that we call it the Laughlin dielectric. For this model, for example, this happens at about when the radius is half, okay? But the most amazing thing is as you keep sending the radius to 0, the critical temperature maps to filling 1/2. So all the Laughlin states crystallize. eventually, once the radius is sufficiently short. Okay, but what is this insulator? So it's some kind of new state in which the electrons are now freezing their positions. Is it just a trivial kind of charge density wave? No, it's not. One simple way to see it is the charge of the quasi-hole, you can compute it, and now it's on continuously changing function. So this insulator will have a dielectric constant, right? It's like the atoms have some polarizability, so there is a continuously changing polarizability epsilon. And when you compute the quasi-hole charge, it ends up being 1 over m, the same you have in the Laughlin state, 1 minus epsilon to the minus 1. So it's some function that changes continuously with the radius of the solenoid. So it's very strange. You should not have, you know, quasi-particles with continuous irrational charges in a gap state of matter. You can compute correlation functions. Correlation functions decay like power laws. So all of this indicates that this state is not a gap state of matter. It's a gapless state of matter with power law correlation. Let me maybe continue because I haven't even started the Moore read and I'm so behind in time. Power law correlations, continuously varying exponents. It's not clear what this state is and if it's even a fully stable phase of matter. Currently, I suspect it's more like a plane of critical states. We're still trying to understand it, but it's, you know, a very weird state. Okay.
Do you know the energy of this excitation? Is it finite?
The quasi-hole, you know, depends on which is the Hamiltonian, because I'm dealing with the ideal wave function. If you write the ideal Hamiltonian, the quasi-hole would have also zero energy. But,
okay, but for Coulomb,
I don't know. Yeah, for a real Hamiltonian, I don't know.
The key question is it finite, right?
The main question is this even a stable phase of matter? And if I add a perturbation, will it become a different state? That's the part that I still even don't know. So it's a bit subtle. Anyway, we even realized after this, we went back to this state below 1 over 70, and we thought about it more carefully, and we realized this state is actually not a crystal. This state is better thought as a nematic fluid, because it's a kind of crystal that you have to think through the lens of Halperin-Nelson theory of crystals at finite temperature, so it doesn't have true long-range order. This state below 1 over 70 is more like a nematic fluid, but let me skip that. I can comment on it if anybody wants at the end and go into the Moore read discussion. So let's consider now the plasma mapping for the Moore read state. This plasma mapping is supposed to work for a different version of the Coulomb gas, the so-called two-component Coulomb gas. This is the Coulomb gas in which both the positive and negative ions are statistically fluctuating. So you just have an ensemble of positive and negative ions. One thing that is crucial for the two-component Coulomb gas is that because now you have attractions, before in the other plasma mapping, you only had repulsions between the electrons. It doesn't matter what happens with the repulsion at very short distance. The partition function, everything is well defined even when you take the size of the ions to 0, when they're only repelling. But when they're attracting, that's very problematic because the Coulomb has now a divergent core. You know, the electrons, you know, the positive ions really want to see where the negative ions are. So the Coulomb gas generically does not make sense as long if you don't introduce a finite cutoff, so like a size of these ions. That's a very important point first. So what was the problem with the previous plasma mapping, or what is the problem, okay? Let me first kind of describe what was the conjecture. So this is the phase diagram of the two-component Coulomb gas as a function of temperature. It has a BKT transition at 1/4. Here I'm using units in which the charges are 1. This is where all the charges are bound into neutral molecules. Then, at, you know, the BKT state disappears into a plasma, but this disappearance into a plasma does not happen in a single stage. Actually, what happens, and this phenomenon is not that fully understood in some sense or fully studied, or the plasma, you know, first ionizes only a very small fraction of all the particles. Those particles form now a plasma, the subset that is ionized. They screen, but in this regime, the screening length is extremely large compared to the interparticle distance because most of the particles are still forming molecules. The plasma only becomes really like a more classical, like Debye kind of mean field plasma at a temperature that is 2 times BKT. So the conjecture that they had made is that if you take the Coulomb gas and you park yourself exactly in the middle of this complicated region, this collapse region at temperature 1/3, and you integrate out the weight of one species, let's say the negative ions, the remaining sort of probability for the other ions will equal to the square of the Moiré of the Pfaffian wave function.
Inti.
Five. Yeah. But this is very problematic. Okay, they were imagining that this radius was sent to 0, but as I said, the radius of the ions, the plasma only is well behaved when you send the radius to 0 if you're in the hot plasma region. In this region, if you send the radius to 0, the partition function is actually, divergent, ill-defined. You always have to keep the radius small but finite to make sense of the plasma in this collapse region, precisely because of this tendency to form a two-species kind of state of molecules and ionized particles. So, then I harassed Victor, as I said, for a long time. This was the formula they had. That formula cannot be right. So he came up with this more elaborate formula. And the formula is as follows. So it captures the physics of that collapse very explicitly and very, very nicely. So we're imagining, again, this plasma at some very specific temperature. What is happening is most of the particles are binding into these molecules and some subset is remaining ionized. And so the conjecture is if you integrate out the positive particles and you get now the weight of only, let's say, the negative particles, that weight decomposes into a sum over different fractions that are ionized. It's kind of like even if this total ensemble is canonical with a fixed total number of particles, it sort of breaks into two ensembles just with fixed chemical potential, because there is a kind of molecular chemical balance between the ions and the molecules, right? So you don't have a fixed number of particles making up a plasma or molecular component. That's why you need to sum over all the components, and the formula is basically expressing that the particles that remain ionized, so here you have total number of particles n, and 2J particles are 2J are in the molecules and the remainder are ionized. The ones that are ionized have correlations given by the square of the Pfaffian. We tested this formula numerically. It works. And this formula matches very well with a mean field theory that was constructed by Fisher, Lee, and Levin to understand this collapse. And it's a kind of, analysis, a kind of mean field analysis in which you just try to find the density of molecules and ions by solving a kind of chemical balance between both of them, and that gives you the proportionality. So the conclusion, for example, at beta equals 3 from this mean field theory is that the density of plasma is always parametrically smaller than the density of molecules. It scales like the square of molecules. Most particles are in the molecular component. And here is a point where actually I think we have done something that is useful to classical physics. That's why the title has the, gifts from Coulomb gases to quantum Hall and back. So this is the part that is back, because here we can do the calculation very easily using BCS theory, because we're saying this component just has a probability that is equal to a BCS wave function, which is a function for which you can compute correlations, So we actually can even correct this Levin-Lee-Fisher theory now with BCS corrections. And we have found a logarithmic correction to this scaling. But, the essential theory is there, but we can compute, corrections to the pressure of the plasma, by using BCS theory. So the summary of this part is that basically what happens, what makes the problem complicated is that Coulomb gas at that temperature wants to break into two components. Most of the particles actually still want to bind into molecules. A very rare dilute subset remains ionized, but that subset that remains ionized has the same correlation functions of the square of the Pfaffian BCS wave function. It's a more, elaborate version of the mapping. But, that's just the BCS wave function. Let's try to go back to Moiré. Okay, so what was the conjecture for Moiré? Again, the previous kind of not correct conjecture was that you just integrate out the positive ions, you get the Pfaffian. So the idea was you glue to this Pfaffian just the Laughlin wave function. So all you have to do on the right-hand side is add some extra interactions to the particles in the plasma. So you have to modify the plasma from gluing this Laughlin part. This gives an extra interaction. And it's what you have to do is basically give another kind of charge to the particles. So in addition to the usual two-component Coulomb repulsions, basically the red particles, the ones that are the zetas, have an extra repulsion that is coming from gluing this Laughlin part, and you also have to put like now a neutralizing background. It's complicated. So, but it was believed that after you do this, this plasma would have the same correlations of the Moiré state that was, even used to try to, compute correlations of that plasma. And the hope was they would be computing things about the Moiré state, but unfortunately that doesn't hold. Now the situation is very complicated because if we apply this corrected formula, what we get on the right-hand side when we glue the Laughlin part to this side is actually a very complicated mixture of a wave function that has bosonic and fermionic character. So it's like the subset of particles that was making before just the molecules now gets dressed by the Laughlin part. So they become strongly correlated. And the ones that were ionized, they get dressed with the Laughlin part, so they become the Moiré part. So it's kind of like having a wave function that is a Bose-Fermi mixture of, some particles that are bosonic and have a Laughlin wave function, some other subset that is more dilute and has a Moiré wave function, and also some species correlation. So it's a Bose-Fermi mixed particle. It's interesting, but it's not clear, how to construct then a mapping that would, by doing classical StatMech, give me the correlation functions of the original Moiré state at least. Okay, that's it. That's just the summary of everything. So I'll leave it there for you to read. Thanks.
So when you go through this, I understand the wave function transition, you're not breaking any rotation or
asymmetry breaking at all.
I see. So it's just, but that's because of the melting. You cannot.
It's a BKT transition, and all that is happening is the ion is binding and binding. It's kind of like what happens in BKT, that there is binding and binding, but the symmetry
is decrystallization or
it's a crystal. But you see, the plasma has the same symmetry. So the charge density, because the ions are there, is going to have some kind of bumps even in the plasma. And what happens once you crystallize is these bumps become very large.
Okay.
But symmetry-wise, there is no change.
Okay.
In the two-component phase diagram.
Yeah.
So the second point between the weakly ionized and strongly ionized, is that a transition or a crossover?
It's a crossover, but here is something very interesting. Oops. This is a non-analyticity only at A going to 0. So the partition function has a non-analyticity at A equals 0. But as I said, to make sense of a problem, you always have to be at finite A. So when you cross let's imagine this y-axis here is like A, right? So if you cross
A is the
radius of the ions. If you have any ions with a very small but finite radius, you will have a sharp BKT transition and a crossover here. But the crossover becomes increasingly sharper the smaller the radius.
I see.
So there is a very clear change, okay? The plasma really changes there. Even though it's a crossover, it can be quite sharp if the radius is small. So I think this phenomenon maybe has interesting implications even for super fluids. This is what I was, telling Matt. It's like when you think about this as super fluid, you see it's like super fluid is where all the particles are bound, right? This could be like a quasi-superfluid because most vortices are still bound. So locally over some length scale, it still looks superfluid, but eventually a few of them are ionized. So it's a normal state with dissipation. But you see only the dissipation at very long distance.
Any questions? Okay, if not, let's continue again. So for the next Okay, so our next and last speaker today is Eslam Khalaf from Harvard University. Who tells about the dynamics of dispersing anions in fragments, microscopic origin of binding and dispersion.
Yeah, thank you. Yeah, so let me start by thanking the organizers for inviting me to this very nice workshop. I really learned a lot. And thank you all for staying till the very end. So I'm going to talk today about some recent work about the dynamics of dispersing anions. And the main motivation of this work is this remarkable discovery a few years back of a fractional quantum Hall effect without magnetic field. First in twisted MOT2 by Xiaodong Chu's group, and then in rhombohedral graphene by Long's group. And of course, you know, from an experimental viewpoint, there's a lot of exciting new things you can do with the system once you have quantum Hall effect without magnetic field. But as a theorist, you can also ask the question whether there is really qualitatively new physics that's possible in the system that wasn't possible before in fractional quantum Hall. And there is a few qualitative differences. For example, one of them is that time reversal symmetry is broken spontaneously rather than explicitly, and this could lead to interesting domain wall dynamics. But my main focus today would be on some other distinction, which is related to the fact that continuous magnetic translation symmetry gets broken down to a discrete one. So this turns out to have kind of very far-reaching consequences for the dynamics of excitations in the system. So there's a very kind of elementary argument that continuous magnetic translation symmetry forbids any dispersion for any charged quasi-particle. The intuitive part of it is just that charged quasi-particle have cyclotron orbit, but formally you can think that continuous magnetic translation acts as a boost in momentum. So it relates the energy at momentum k prime, and this doesn't allow any dispersion for charged quasi-particles. And as a result, although in fractional quantum Hall we have all these very exotic quasi-particles, the anions, they cannot really move. So they don't have any non-trivial dynamics. On the other hand, when we have quantum Hall in a lattice, we break the symmetry, so anions are kind of more free, so they are allowed to move. And we can get new interesting physics from this anion dispersion. And this led to the revival of an old, but very exciting idea that was first proposed by Laughlin in the late 80s, and then by many others, and was revived recently in some very nice work by Shi and Sentel, where and this idea is that an anion gas has some an itinerant anion gas has some interesting natural instability. And the idea is the following: so anions can never really form a gas because they always interact with each other through statistical Chern-Simons gauge fields, which mediate very long-range interactions. But one way to think about them, these interactions, is that each anion sees each other anion as a flux tube. So if I'm at a finite doping, this excess statistical gauge flux means that the anions are living in Landau levels of their own statistical gauge field. So this gives us a kind of Landau levels that have a very interesting property, which is that they are at a fixed filling fraction because the magnetic field is tied to the density of the anions. And it turns out that if this filling fraction is an integer, so we're filling an integer number of these Landau levels, the gap state is generically a superconductor. And there's a kind of a simple argument, qualitative argument to see this, which is that if I try to add extra magnetic field in this state, I ruin this relation between magnetic field and density, and this pushes some particles across a gap, so it gives an analog of a Meissner effect. And of course, you can have a more kind of sophisticated argument to show that this is indeed a superconductor. And the modern iteration of this argument have pointed out kind of a few important details. One of them is that the action of translation on anions is fractionalized, which means that for example, for the 1/3 state, this anion dispersion has to have 3 valleys. And then the state we realized actually turned out to depend on the kind of anionic excitation that is cheapest. So for 2e/3 anyons, so if the elementary e/3 anyons bind first and then live in some dispersion, then the resulting state is a superconductor. While for e/3, you get more complicated states. You can also get a superconductor, but it's not a given. So here you can get other states. So we were very interested in the story, both from trying to understand microscopically how do you get these kind of dispersion and binding of anions, but also to understand whether aspects of experiments like disorder could really affect this picture. How would they affect this picture? So we already started thinking about this problem when actually this very nice experiment from Shanghai group appeared, which seems to have observed which observed superconductivity upon doping a fractional quantum anomalous Hall state in twisted MOT2 at 2/3. Now, I don't want to make a very specific statement about whether this is also relevant to rhombohedral graphene, where superconductivity was also observed, not in the same samples, but in the vicinity, in the same parameter space next to fractional quantum anomalous Hall state. So my focus would be really on this case of twisted MOT2, where I have a 2/3 state, and upon doping, I get a superconductor. And I want to emphasize just so this here is the 2/3 state, and then when you dope, you actually get on one side you get a superconductor, and on the other side you get a reentrant integer quantum anomalous Hall state. And these two are they are separated by highly resistive regions. So there is these resistivity peaks that separate the fractional state on both sides from the superconductor and the reentrant state. So the first thing we start thinking about is how whether this is consistent with this anion superconductivity story. And clearly the stuff that are not obvious, at least, is how you get the reentrant quantum anomalous Hall states, and why do you get these resistive regions rather than just directly transitioning to this superconductor. And it turns out that just by including the effects of this order, at least you can qualitatively understand most of these aspects. So just let me just very briefly review how does this order affect lambda level. So when we want to understand this order in lambda levels, we have a main parameter that controls the strength of this order, which is omega c tau. And if omega c tau is much smaller than 1, this is the limit where this order washes out the lambda levels. And whatever delocalized states responsible for the response are just pushed above the chemical potential. So we don't get any Hall response, any non-trivial Hall response. While in the opposite limit, we are in the limit where lambda levels are well formed. They're below the chemical potential, and they give us the Hall response. And the transition between the two is a standard plateau transition. So when we apply this to the anion problem, we find that this relevant quantity depends on the anion mass and the anion density in an interesting way, because omega c, so omega c of these anion lambda levels is really b over m, and b is the anion density. So, so for example, in the limit when the anion mass is infinite, which is what happens in the lowest lambda level, we're always in the strong disorder regime. So these anion lambda levels never really form. You never really see them. On the other hand, when the mass is sufficiently small and the density is not, the doping of anions is not extremely small, then I can get in a regime where this weak disorder regime, where I get the response of these anion lambda levels. And the two are related by a plateau-like transition associated with these delocalized states crossing the chemical potential. And this offers a qualitative explanation for these resistive regions. In the paper, we tried to be a bit more quantitative. So we took kind of a simple mean field picture, or we took a simple picture where we ignored all the gauge fluctuations associated with the anions, thought of this as an integer Hall transition, and just translated the anion to the electron language. And we find at least reasonable agreement, even in some quantitative aspects. And a simple scenario that can explain these observations phenomenologically is that on one side, on the side where you get these reentrant integer quantum Hall states, you're actually doping E/3 anions. And if you have sufficiently strong valley mixing, or if these field disorder that's not smooth, then it's possible to have only one delocalized state crossing the chemical potential. And once you have one delocalized state crossing the chemical potential, you get a reentrant integer quantum anomalous Hall state. On the other hand, to get the superconductor, you need to dope 2E/3, and you need all three delocalized states to cross the chemical potential. So this is kind of a nice picture, but of course, if we really want to be serious about comparing to the experiment, we want to understand all of these aspects from a more microscopic perspective. That would be the main part of my talk. So this was kind of more the introduction and the motivation. Why do we want to think about the microscopics of these objects? And by microscopics here, I mean the anion binding and the anion dispersion and how they lead to these various phases. So my goal is to develop a microscopic theory of these itinerant anions. And I want to just, from the beginning, I want to kind of contrast to two different approaches, two kind of opposite extremes. One of them is to try to kind of brute force numerically simulate this whole system. And of course, that's a very that gives us very valuable insights, but also there are some challenges. For example, in ED, we're limited to small system sizes. So we already can do only a few number of electrons. And then if we want to dope some number of anions, it's kind of very hard to put in the system more than a couple of anions. Also, when we get something out of that, it's not always physically transparent what's going on. And one reason for this, which you can view as from some perspective as a feature, but from other perspectives as a bug, is that these treatments usually include all details of the theory. So typically we have a spectrum, an ED spectrum like this, but all the anion physics is really happening in the low energy sector. So following the logic, we always apply to all kinds of problems. If we have a low energy set of degrees of freedom, we want to kind of project onto those and not include all kinds of high energy states into our formulas. So that's one kind of extreme, just including everything. There's the opposite extreme, which is kind of just includes only the very long distance topological aspects of the problem. This is very good at accessing kind of the universal physics, but it cannot really access all the short distance physics. And for the questions of binding and dispersion, this short distance physics is crucial. So what I want, so my goal, which I'll present some of the results towards this, is to develop a microscopic theory of anions. And I want this theory to satisfy the following requirements. So first, if I think the anion physics is the relevant physics, and if I want to understand what are the implications, I want a theory that only contains anion degrees of freedom. So I want to project onto this space. I want this theory to be analytically controlled, which means that it should be derivable from a microscopic model in a well-defined limit. I could apply it slightly outside its range of validity, but at least I'll have this certainty about certain parameters in certain points in parameter space where I'm sure that I'm doing something valid and correct. I want the theory to capture the short distance physics that's responsible for dispersion and binding. So I cannot just do the typical long distance Chern-Simons where I replace the anions by flux tubes. And I want to be able to reproduce the kind of universal long distance physics. So it also should be natural in the theory to see how this Chern-Simons physics appears. And finally, I want to be able to have quantitative comparison to the experiment. So the first part of the theory, which is to try to write a theory of only anions, it turns out that there's a kind of a very nice framework that already Inti has reviewed in the previous talk, where we can start from this idea of ideal or Aharonov-Kasher bands, which are essentially Dirac lowest Landau levels in non-uniform magnetic field. And there's by now kind of a long list of literature that has studied these kind of models and have shown that, for example, for twisted MOT2, they are not actually very far off from the realistic band structure, from the realistic form of the bands close to the magic angle. Now, the nice thing about this, which is also was mentioned by Inti, is that if we are thinking of Laughlin state and doping some quasi-holes, then there's specific interactions, these Strugman-Kivelson interactions, which are essentially some truncated expansions of short-range interactions. for which we can write an exact wave function for any number of quasi-holes. So these she's are the quasi-hole coordinates, and here these she's are complex. Then what I can do to get a very controlled way to project onto this manifold of quasi-holes is to consider an interaction that has a Truman-Peterson piece with a large prefactor plus a leftover piece. And as long as the leftover piece is small compared to this alpha, I have a parametric separation between the gap scale and whatever happens in this anion space. Of course, this is kind of a theorist trick, but this is actually a very good model for any true short-range interaction. So for a true short-range interaction, I can show that this expansion is always valid. But if I just look at the numerical spectrum, even if I take a screened Yukawa screen Coulomb with a screening length equal to 1, I still get a reasonable separation between the gap scale and the kind of the leftover scale. This is a good approximation, even away from the limit where it's fully controlled. And my goal now is to project V onto the space of Laughlin quasi-holes. Now, the main complication when projecting the interaction of the space of quasi-holes is that this space of quasi-holes is the D-wave function. Yes?
You have small scale of V. Alpha is dimensionless. So separation between low energy and high energy, it's alpha times what energy scale?
Yeah, so it's so this gap scale will be controlled by the matrix elements between that connect. Let's see. So I mean, I've been a little sloppy here. So alpha here is dimensionless. Of course, it's multiplied by a dimension full scale that is the gap of VTK. So VTK itself, the Truman-Peterson potential itself has a gap. So with this alone, this will have a gap of order 1, or order whatever units I'm writing VTK, and then I'm scaling that gap by alpha. Yeah. So quasi-hole wave functions are non-orthogonal, and so this leads to a situation we are familiar with. Actually, this is what always happens when we project on the lowest lambda level. So when we project the lowest lambda level, we have an interaction that itself is simple. It's just a density-density interaction, but we project it onto a band that is non-trivial. It has a non-trivial quantum geometry, as Jabin discussed yesterday. And this quantum geometry and topology also of the band leads to all kinds of the non-trivial quantum effects of the lambda level. So we no longer just have a classic electrostatics, but we have a lot more exotic effects. And in a sense, what I want to do is I want to do the analog of Landau levels and Landau level projections, but for this Hilbert space formed by anyons rather than by single particles. So in a sense, I want to introduce a notion of anyon quantum geometry or a many-body quantum geometry, where really there's a many-body in the sense that the magnetic field felt by each anyon knows about every other anyon. But whereas usually we think of only the anyon topology because we only think of each anyon seeing the other as a flux tube, this is really a notion of an anyon geometry, the quantum geometry of the anyon Hilbert space. So how do I perform this projection? So I want to do it in a way that respects all kind of the nice analytic structure of this anyon Hilbert space. And so one way to do this is to think of promoting these anyons to dynamical variables, these anyon coordinates to dynamical variables, and noticing that, so this will give me a manifold. This manifold is parameterized by the coordinates of the various anyons, and it turns out that there's a very nice structure I can define on this manifold. It's called a Kähler structure. So Kähler structure, just I take this overlap of these holomorphic wave functions. So once I take this overlap, I've already integrated out the electrons, so I'm only thinking in terms of anyon coordinates. And I find that this is a Kähler manifold, and a Kähler manifold means that it's a notion of ideal quantum geometry. It means it has a complex structure, a metric structure, and a very curvature structure, and they're all tied together. So so this is kind of a many-body version of this notion of ideal quantum geometry that Inti had mentioned, where the metric and the very curvature are tied together. But now both of these are now many-body objects. And now I can write not an effective theory. I can write just an exact theory on this manifold. So I take my Hamiltonian and I project it onto this, and I write the evolution as a path integral. And this path integral will have a Lagrangian that has two terms. One of them is this anion Berry phase that encodes the both the background field and also all the statistical fields felt by the anion. And the second is the projection of the potential on this space. And what would make this very kind of also a very useful, not just in a conceptual way, but a very useful way to actually compute things is that these two objects, they can be easily computed from Monte Carlo using kind of the plasma analogy. So this can be done for any kind of anion configuration. Of course, these simplify at long distances due to plasma screening. But if I'm interested in the short distance physics, I will not do this. But this already makes it very easy to relate to the long distance physics. And if I want to really look at what the physical content of this anion Berry flux, I find that it has many pieces. So it will have a background piece. So if I have a lossless state at 1 over Q, then there's a background piece that tells me that the anion fields of a uniform background field of 1/3, for example. There could also be field modulation that come from the fact that I'm considering Landau levels in a non-uniform magnetic field. But importantly, there's also kind of a many-body piece, a many-body Berry flux piece. And this really reduces to the Chern-Simons at long distances, but I can actually consider it for any distance. So this is kind of a smeared version of Chern-Simons that accounts for the fact that the holes are not really flux tubes. They have certain volume. And so it turns out, so generally, if I have a path integral, it's kind of this is a kind of a first order path integral because it doesn't have a kinetic term. So the quantization of this can sometimes be tricky. But when you have the scalar structure, there's a very kind of neat way to do this. And I'll go through it quickly. It's kind of a generalization of the Landau level projection, but for this case of very many-body quantum geometry. So you have I can identify my Hilbert space with the antiholomorphic function. The reason they're antiholomorphic because anions has kind of opposite charge to the electrons. There is a way to define inner products using something called the reproducing kernel.
Question?
Yes.
So you have a path integral in terms of like single and neon coordinates.
Yes.
On this weird Hilbert space. If I try to think about it from a canonical perspective, what would like the commutation relations for those coordinates look like?
Yeah, it is complicated because the canonical commutation is like the magnetic field, but the magnetic field itself depends on all other anion coordinates. So if I take, if I have only this term, this will be each one will have kind of a harmonic oscillator or lowest Landau level projected canonical commutations with LB squared scaled by Q. But now you have this. So if you try to write just the canonical commutations, they will look quite complicated. So you can only deal with the canonical commutation in a semi-classical way if you assume all the fields change slowly over space. But this scalar formalism completely sidesteps that. So I can't construct the Hamiltonian without having to worry about that.
So for instance, the symplectic form you're saying depends on how many anions there are to begin with?
The symplectic form depends on the locations of all anions.
Okay.
So it's yeah. So that's why I kind of prefer to do it within this framework. So this framework, you can just think of it as a dictionary. Like we know how to form an anion Hilbert space. We know how to form for any classical potential. We can construct an operator. And once we have solved the anion problem, we know exactly how to map it back to electron coordinates. So using this framework, So my goal is to develop a theory that goes from the very microscopic all the way to the response at the end. So I want to start from the 1 to the few to the many. And what I will present today is mostly about 1 and few. The many is still in progress. So for the 1 anion problem, I want to understand how I can get dispersion of the anions, starting from an Aharonov-Kasher band with some interaction projected onto it. For the second part, I want to understand how this binding emerges. And it turns out the binding problem, although it's an elementary problem in the Landau level context, that it hasn't really been discussed that extensively except in recent work. So I'll spend most of the time for the binding problem on the actual classic Landau level. And again, the results for the band case for binding is still work in progress. So let me start with the single anion problem. So for the single anion problem, I have within this formalism, kind of things simplify because I have the magnetic field felt by the quasi-hole. It's just one quasi-hole, so it just feels the magnetic field. That's part of it is a background, and part of it is just some periodic modulation. Then from projecting the interaction, so I don't have really bare dispersion, but from projecting the interaction onto a band that breaks translation symmetry, that breaks magnetic translation symmetry, I will generate a periodic potential for the quasi-hole. And then, so I just want to construct a dispersion out of these two. And the idea is, if I first, just to get an idea, if I ignore these periodic modulations, then essentially this magnetic field allows me to define some guiding centers for the quasi-holes. And what the guiding centers mean is that the x coordinates for the quasi-hole and the y coordinate for the quasi-hole are canonically conjugate to each other, which means x is the momentum conjugate to y. And that basically allows me to turn a potential energy into kinetic energy. So if I start with a potential, I can turn it into an operator, but this operator, if I diagonalize it, I find it's diagonal in momentum space. So this gives me an expression for the dispersion. Of course, if I want the full expression for dispersion without this assumption, I need to use this geometric quantization formalism, and then we get a complicated expression just in terms of the Fourier components of delta B and V that I will not mention here. But also, I'll discuss another way to see how anion dispersion emerges that's maybe simpler, more intuitive. So the other way is to notice that if I look at this Hilbert space of anions, like these anion states, they are labeled by one parameter. They're actually some kind of coherent states. Actually, they are exactly coherent states of magnetic translation. If you look at the definition of coherent states for magnetic translation, you'll find that they have to satisfy this condition, and overlaps and everything can just be computed from. You don't need to do any integrals. All these overlaps can be computed from representation theory. But the important thing to notice is that the magnetic algebra has this factor of 1 over q, which is this the fact that kind of translation is fractionalized for anions. And one way to see this, or one consequence of this, is that the unit cell for translations that commute has to be enlarged by a factor of q, or the Brillouin zone has to be folded by q. But just knowing this, I can construct, just explicitly, I can construct momentum eigenstates of these quasi-holes that are simultaneous eigenstates of all the translations or lattice translations that commute. And just from a simple counting argument, we can show that the distinct commuting translations that also preserve the topological sector is the same as the number of quasi-hole states, which tells me that there would be really one band of quasi-holes. But this band, due to this folding, will have to have q-fold degeneracy in the reduced Brillouin zone or q-squared fold degeneracy in the full Brillouin zone. And then you can just Monte Carlo sample that object. There's a few technical issues with that, but we managed to overcome these, and then you can have the results for the kind of the anion dispersion. And you see here the approximate 9-fold degeneracy, so it only emerges exactly in the thermodynamic limit. And here I'm showing the anion dispersion for a toy model, where I'm just modeling these variations in the magnetic field or in Moiré curvature by just a simple cosine, and I'm just tuning its strength by a parameter. And you see, as I increase this parameter, this very inhomogeneity, the bandwidth of the anion band increases. And just I want to emphasize that this anion dispersion was generated purely from the interaction and non-uniform quantum geometry. So the original bands were completely flat. So I can get back now to twisted MOTE2, which is kind of what was the motivation of this. So we can first see kind of what is the typical magnitude for a realistic numbers of this bandwidth. And we found that this bandwidth is around 1 MeV. It becomes a minimum around the magic angle because of quantum geometry and because of bare dispersion effects. But overall, it's not a small bandwidth. So this is suggesting that this anion dispersion in sufficiently clean sample should be relevant to the physics of twisted MOT2. One thing we can see is that this bandwidth of the anion bands increases as I apply displacement field. And this we can understand from the fact that this anion dispersion comes from the fluctuations in the Berry curvature. And as I increase the displacement field, usually the Berry curvature becomes non-uniform. I mean, eventually we get a transition to a different kind of band, but before that, the Berry curvature becomes non-uniform. So the bandwidth of the anions is expected to increase. And if I try to at least compare this to the experiment, of course, so far we only have this one experiment, so it's what we'll have to work with, but there will have to be more experiments to substantiate this. And if we really think of the E/3 anions, where so far this is what I've been focusing on, the prediction out of this is that the phase boundary associated with the E/3 anion should move inwards as I increase the displacement field, because this phase boundary is really controlled by how big the mass is. And as I make the mass lighter, I should transition at smaller density. And this seems at least consistent, at least the qualitative trend. So next, I want to discuss the few anion problem. And this few anion problem, I will discuss it in the context of low Landau level, because it turns out that even then, this problem is actually non-trivial. So again, we can use our formalism here. The center of mass is trivial, so we can think of everything in terms of a relative coordinate. And now we can compute, the quantities that enter the theory. You can compute everything exactly, so or from Monte Carlo. So this is the potential between two anions as a function of the relative distance, and this is the magnetic field one anion feels as a function of the distance from the other. So you see that at long distance, this will approach 1/3, which is the background. And at short distances, this is actually what in Chern-Simon's description would be a delta function. So here we are kind of the theory can capture the fact that these flux tubes are smeared; they are not just concentrated at a point. And then so we need to just solve a two-body problem in a Landau level with this magnetic field with this potential. Now, initially, you may think, okay, you look at this and you think, okay, there would be no bound state. This is a repulsive potential. It's positive everywhere, and it's repulsive. And by the way, my definition of a bound state is a state whose energy is lower than the energy of two infinitely separated holes. But surprisingly, if you solve this two-body problem in the lowest Landau level, although this interaction looks repulsive, this two-body problem has a bound state. For some interactions, you cannot see it easily from here, but for some interaction, you can get a bound state. And I can go into more detail why that is the case, but I'll now just show you the results. So you can just construct the Hamiltonian. It says you can construct the Hamiltonian using this geometric quantization formalism and look at the spectrum as a function of the relative angular momentum, and you see that provided that the screening length lambda is smaller than 6, you get clearly these bound states. The prominent bound states are in the even relative channels, like all the channels are even, but the prominent ones are at 2 and 6. And the 1 at 2 persists to relatively large lambda, but I want to emphasize that this is actually a fully controlled calculation, and we can do this Monte Carlo extrapolated to the thermodynamic limit. So we have very good, we can make sure we're converged. We go to very large system sizes, like 100 or 200 electrons. So this is, in a sense, I would say in the limit where this is valid, this is a definitive statement that anions, the quasi-holes of Laughlin state for screen interaction form a bound state, which is a non-trivial, sorry.
If you just go back to previous slide and take partial component of this repulsive interaction for L equal to 2 and L equal to 6, will you get attraction?
Well, if you just look at this alone, no. You have to also account for Berry curvature. So the way you do it is you do this analysis, but account for a Berry curvature as well, and then you find that component is some Laguerre decomposition of this, and then some of these coefficients can be negative. There is one, but so I want to just emphasize that this bound state is a momentum eigenstate, so it's a superposition of these states. So if you look at just any fixed classical configuration, you find that the energy is positive, but there is a superposition that benefits from this quantum geometry or Berry curvature. And there is a way to see it in in terms of electron density. So if you look at this electron density the electron density correlation function in one of these states, in this bound state, you'll find that it has a diff at short distances. So if your interaction is short range, you can, yes.
Do you also see a bound state for L equals 0? Is there an S-wave bound state?
No. L equals 0 is repulsive, so it's always repulsive. It's here. Yeah, it's always repulsive.
Can you think of the physics that's similar to like Cohn-Luttinger physics for Cooper pairs?
Yeah, I think
you have some.
It is similar to Cohn-Luttinger. Cohn-Luttinger, when you don't have you have this kind of quantum geometry or very field not on top of a lambda on top of Fermi surface, but yeah, it's Cohn-Luttinger like yeah.
I guess in Cohn-Luttinger you do something else for the interaction. You generate it. Here you have interaction. You just take different different partial components plus Berry curvature.
Yes.
So in this respect, from the very beginning, you have this attractive interaction.
Yeah, but what I want to say is just, well, of course, the attractive interaction wasn't there in the microscopically. So the electron-electron interaction was purely repulsive. And also in this projected anion coordinates, also it looks purely repulsive. But you have to decompose it into these particular channels to see that attraction. Yeah. And of course, so we can do all this also for 3 and 4 quasi-holes. And here we have to compare, like, in order to define a bound state, we have to compare it, for example, for 3 infinitely separated E/3 quasi-holes or 1 plus 2. So, and we seem to still at this screening, we seem to still find bound states. And in fact, if we look at this very first, the smallest L, we get a bound state. This is described by this wave function for quasi-holes. So this actually looks like a region of nu equals half bosonic Laughlin of these quasi-holes. It is a region of a 2/7 state, like this new bosonic Laughlin. If you take this wave function for enough holes and integrate out the whole coordinates, you get the 2/7 state. So now this was the question. I mean, this doesn't look like small bound states. It looks like phase separations. It looks like whenever I put quasi-holes, they want to cluster in the middle. And that's something, if you just did ED for a small number of quasi-holes, you wouldn't be able to tell. So is there actually a regime of free 2/3 bound state? So what we did was we looked at up to 6 quasi-holes, and we looked at the energy per particle.
So
yes.
But 2/7 is what? That's not Jane states. What is this?
It is a Jane state. It's
fifths.
No, 2/5 if you do 2/5 is larger than third. 2/7 is smaller than third. So you can look at the energy per particle for up to 6 quasi-holes, and then you find actually regimes where these bound states are stable, in that there are bound states, but they like to be far away from each other. So we find, for example, some even odd effect in some region of the parameter space. And these are objects that should be visible in STM experiments. They have very, very different charge profile from the simple quasi-hole. Yeah, I'm very close. So for example, this 2 quasi-hole bound state is, rather than a dip in the charge, it's actually a peak in the charge and then a ring around it, a ring of reduced charge. And for the 3-1, you have kind of more features. So separate from whatever the application of this to this MOT2 problem, we can also use this approach to understand the different kinds of bound states people see in bound to defects in standard quantum Hall systems. And yeah, as I mentioned, so the Chern band case, we are still doing the calculation, so I don't have like figures to show, but already from the 2 calculations we did, it's not hard to predict what would happen. So we add this modulation, so we get a kinetic energy, and clearly the kinetic energy will favor the lighter particle. All these phase boundaries are expected to move to the left. So this region of possibly phase separation should be killed once I add some non-uniform quantum geometry, some modulation. Now, yeah, as I said, I will not really have time for the many anion problem. I just wanted to mention very briefly that, in the classic theory of anion superconductivity, you write a Hamiltonian like this. You don't derive it microscopically, but you write it. And then you can ask if we try to derive it microscopically within our formalism in the dilute limit. Turns out we don't get exactly the same Hamiltonian. We get an Hamiltonian that is actually a many-body Aharonov-Kasher Hamiltonian. And the reason for this is that because anions have their own Berry curvature, even a single anion has a Berry curvature from the background, there is an additional orbital magnetization piece that enters the Hamiltonian. And that means that I think there is a controlled way to get a parameter regime for which we can prove that the ground state is this 2e/3 anion superconductor. But that's still work in progress. And then let me close by acknowledging all the students and postdocs who contributed to this. Yeah.
So, I can start instead of with a non-uniform magnetic field. I can start with just electrons in a magnetic field, strong magnetic field, filling of 2/3, let's say, or close to 2/3.
Yeah.
And then turn on a periodic potential with the period Max quantum. So then, as I turn on the periodic potential, at some point you expect to have a transition to a superconductor. So I lose the full conductivity, which is d squared over h times nu, and it becomes 0. That's and the longitudinal conductivity, instead of being 0, becomes infinite.
So I just want to make sure I understand the setup. So in the 2/3 state itself, of course, if you increase the modulation, at some point you lose the state. So you want to be still in the region where the 2/3 state is stable and look next to it.
Right.
Yeah. So initially you have like at a bit of doping, you have, for example, if you have a bit of disorder, you have just these holes because they have a very large mass, they would be localized. And then at some point you get a transition where their mass. So in this context, changing the periodic potential basically changes the mass. So at some point you will get a transition to the so initially you localize the quasi-hole, so you get the same response at the 2/3 state. That's a standard plateau.
Yeah.
And then at some point you get a resistive region and a transition to the superconductor.
So sigma xx will go from 0 to infinity, and sigma xy will go from 2/3 to 0.
Yeah, I think it should look like what is in the experimental figure. So the row, yeah, both of rows will go to 0 at the superconductor. And yeah, so let me.
Yeah, no, they plotted row. I was asking about sigma.
Just a second. It would look like this. So they're plotting row. You're asking about sigma. What would happen to sigma? I mean, inside the superconductor, the sigma xx would be infinite. But so you're asking what happens in between, like, or one of them will hit it before the other?
At the superconducting state, will I get still a finite sigma xy?
I don't think so.
Just the sigma xx.
I think the theory, like the response of the parent state, is completely gone. It's a normal superconductor, very conventional superconductor. Yeah.
Since a technical question, since you mentioned you're using geometric quantization fairly heavily for all this, have you accounted for the role of the metaplectic correction, and like, does that change the 0-point energies in any way?
What do you mean exactly? Like
usually when you're doing geometric quantization, say for particle and harmonic trap, you don't get the half h bar omega. You need a correction to be able to see that.
Yeah, I think it's incorporated in a kind of in a different way in this approach. So I didn't discuss there's a non-trivial measure. I think that's where this is encoded. But also, this is a case where I know where I started, so I can always, when I derive the Hamiltonian, I can always compare it to actually doing the projection.
I see.
The naive way, which is the expanding in an orthonormal basis. So I can always compare the two. And yeah. Yes.
So, maybe a couple of things. So this two bound state of quasi-hole that has this L equals to angular momentum, then if those pair, I guess you will still need to know how to, maybe the question is, can you then infer what is the pairing of the superconductor?
The pairing symmetry of the superconductor. Well, so I think the pairing symmetry of the superconductor is unrelated to the state these two are in. So at the level of the superconductor, you write a theory where you think of these as extreme BC. You think of these as closely bound states, or 2/3, and they might have well been a point particle. And then the pairing symmetry. I mean, it's a, this is a spinless, valleyless band that breaks time reversal. So I think it will have to be P plus IP.
It'd be like L equals 3 or something.
Yeah, so that's the order superconductor order parameter. I think it would be P plus IP.
Maybe how do you understand then these 2 7s? I got lost.
Why
is there
2 7s or
2
something?
7s?
Oh, okay, so maybe the 2 7s comment. So okay, let me. If you want to describe the 2 7s as a hierarchy state, like a Haldane-Halperin hierarchy state, this is an U equals 1/2 state of bosons. When you think of, in the Haldane-Halperin hierarchy, you think of the anions as bosons, and then it's nu equals 1/2. If you do quasi-electrons at nu equals 1, and you put them in a nu equals 1/2 bosonic state, you get a 2/5 state, and if you do quasi-holes, you get a 2/7 state. So you can just so of course this would be a small region of that. So you can ask how many quasi-holes I can put and still have the natural flux. So you can do a simple calculation. You could do it on the board if you would like, or after. But there is a simple calculation that tells you that this would be a 2/7 state.
Okay.
Let's keep it for discussion. So
Yeah.
Adi.
I'm trying to see if there's any remnant of the band state in the superconducting state. So if you look at the ground state degeneracy on the toes and distinguish between exponential splitting and power law splitting, will there be a 3-fold or 9-fold or whatever ground state degeneracy?
I don't think so. No.
No. So it's completely lost.
Completely irregular superconductor.
It completely lost any connection to the fractional state from which it originated.
Okay, I don't see any more questions, so let's thank Eslam. Neither, so
Okay.
you want to say something else?